Hello, and welcome to Sleepy Science. What if the ordinary world around you is not ordinary at all, but a quiet laboratory hiding in plain sight? What if a cup of hot water can sometimes freeze before cold water? Light can push objects without touching them. Sound can shape sand into patterns. Magnets can slow falling metal in mid-air. And a single drop of water can hover above a burning hot pan, like it has learned how to escape contact. In this journey, we'll move gently through the strange physics hidden inside everyday life. From bubbles that solve geometry problems automatically, to lasers that cool atoms almost to absolute zero, to superconductors that make magnets levitate, to graphene so thin it is only one atom thick, yet strong enough to challenge what strength even means. These are not magic tricks, myths, or exaggerated internet facts. They are real physical effects, waiting inside water, light, sound, heat, electricity, matter, motion, and the quiet spaces between familiar things. We'll explore why soap can break surface tension instantly, why snowflakes rarely repeat exactly, why ice floats instead of sinking, why lightning becomes a chemical factory in the sky, why glass can shatter from the right vibration, and why sand fluids, cracks, smoke, plasma, and chaos all reveal patterns the eye usually misses. So if you're ready to stop seeing the world as simple, tap like, hit subscribe, and settle into the hidden science around you. Because the deeper we look at ordinary reality, the more it begins to feel like the everyday world was never simple. It was only waiting for your attention to become sharp enough to notice its secrets. Hot water can sometimes freeze faster than cold water. A cup of hot water placed beside a cup of cold water should lose the race every time, and that is exactly why the strange exceptions feel so unsettling. You expect the cold water to win because it has less cooling to do. It is already closer to ice, already nearer to the finish line, already halfway down the hill. But under certain conditions, hot water can freeze faster than colder water, and this surprising effect is known as the Mpemba effect. It does not mean hot water always freezes faster. It does not mean heat magically turns into cold. It means that freezing is not as simple as lower temperature wins. Water is not just a number on a thermometer. It is a moving, evaporating, swirling, changing system, and the path it takes toward ice can depend on many hidden details. Imagine placing two identical containers in a freezer, one filled with hot water and one with cold. The hot water begins by losing heat rapidly, because the bigger the temperature difference between the water and the freezer air, the faster heat can flow away. Some of that hot water may also evaporate, meaning there is slightly less water left to freeze. In a small container, that loss of mass can matter, because freezing less water can take less time than freezing more water. Heat can also create stronger convection currents, tiny circulating flows inside the liquid that move warmer and cooler regions around more efficiently. Instead of cooling only at the surface while deeper water remains warmer, the hot sample may stir itself more actively as it cools, carrying heat upward and outward. The container, the freezer shelf, the amount of water, the shape of the cup, airflow, dissolved minerals, and even whether the water supercools can all change the result. Supercooling is one of the strangest parts. Water can sometimes drop below its normal freezing point without immediately becoming ice, because it needs a starting point, a tiny seed, a disturbance, a crystal, a scratch, or a speck of dust for ice formation to begin. So the cold water might quietly slip below freezing and remain liquid for a while the hot water, after cooling down, may begin crystallizing sooner. In that case, the water that seemed behind can suddenly cross the finish line first. But this is where the truth becomes more interesting than the myth. The Mpemba effect is real enough to be studied, observed, and debated. But it is not a simple rule you can trust every time you fill an ice tray. In many experiments, cold water freezes first, just as common sense predicts. In others, hot water wins, but only because the setup allows certain factors to matter more strongly. This is why scientists still discuss the effect carefully. The mystery is not whether hot water contains some secret shortcut to ice. The mystery is why freezing depends on so many small conditions we usually ignore. It teaches you that nature often hides complexity inside ordinary experiences. A glass of water looks calm, but inside it, molecules are moving, colliding, escaping into vapor, gathering into patterns, breaking apart, and rearranging themselves. Cooling is not just a quiet descent from warm to cold. It is a competition between heat loss, evaporation, movement, crystal formation, and the surface where the water meets the world around it. And maybe that is why this effect stays in the mind. It takes something almost everyone understands, water turning to ice, and reminds you that understanding a thing casually is not the same as understanding it deeply. You may have watched ice form 1,000 times, but beneath that simple transformation is a hidden negotiation between temperature, structure, and chance. The hot water does not win because the universe is cheating. It wins only sometimes because the race is not as fair or as simple as it looks. The starting temperature is only one part of the story. The real story includes how much water remains, how the liquid moves, how quickly heat escapes, whether the container touches the cold surface well, whether ice crystals begin easily, and whether the water delays freezing by staying liquid below its usual freezing point. This is why the Mpemba effect is such a beautiful lesson in everyday physics. It shows that the obvious answer can be mostly right and still incomplete. Cold water usually has the advantage, but nature does not care about our simple shortcuts. It follows all the conditions at once, and when those conditions line up in the right way, hot water can do something that feels backward, almost impossible, yet still belongs fully to science. So the next time you see water steaming in a cup, do not think of it as something simple waiting to cool. Think of it as a small world in motion, carrying heat, losing vapor, shaping invisible currents, and preparing for a phase change that depends on more than your eyes can see. The lesson is gentle but powerful. The ordinary world is not ordinary because it is simple. It feels ordinary because you have stopped looking closely. Even freezing water can surprise you when you ask the right question. And sometimes, the thing that seems farthest from becoming ice may arrive there first, not by magic, but because reality is more layered, more conditional, and more quietly intelligent than common sense alone can hold. Light can push objects without touching them. The strangest thing about light is that it can feel weightless while still being able to push. You stand in sunlight and feel warmth on your skin, but you do not feel the light pressing against you the way wind presses against your face. A beam from a flashlight seems too silent, too gentle, too ghost-like to move anything at all. Yet light carries momentum, and when it strikes a surface, reflects from it, or is absorbed by it, it can transfer a tiny push. This push is called radiation pressure, and although it is incredibly weak in ordinary life, it is real enough to move matter, guide spacecraft, shape dust around stars, and trap microscopic objects in laboratories. Light does not need fingers to touch something. It does not need air to shove it forward. It can press by delivering energy and momentum through photons, the small packets of light that make up electromagnetic radiation. A photon has no rest mass, but it still carries momentum as it travels, and that means when light arrives somewhere, it does not arrive empty-handed. It brings a small mechanical effect with it. The reason you do not notice this in daily life is not because the effect is imaginary, but because the push is extremely small. A lamp shining on your hand does not throw your fingers backward because the force is far weaker than gravity, muscle tension, air currents, and all the ordinary forces your body deals with constantly. But make the object light enough, smooth enough, isolated enough, or place it in space where there is almost no friction, and the quiet pressure of light begins to matter. This is the principle behind solar sails, one of the most elegant ideas in space travel. Instead of carrying fuel and burning it like a rocket, a spacecraft can unfold a large reflective sail and let sunlight push it. Each photon that bounces off the sail gives it a tiny nudge. One nudge is almost nothing. Billions upon billions of nudges, arriving every second, can slowly build motion. The acceleration is gentle, but in space, where there is no road friction and no air drag to constantly slow the craft down, that gentle pressure can continue working for a long time. It is not fast in the dramatic movie sense, but it is persistent, patient, and almost poetic in its efficiency. The spacecraft moves because sunlight keeps whispering against it. This same idea appears throughout nature. Around bright stars, radiation pressure can push dust grains outward, helping sculpt glowing clouds and comet tails. When a comet approaches the sun, some of its material is released as gas and dust, and sunlight helps push the dust tail away from the sun. The tail does not simply trail behind like smoke from a moving car. It is shaped by the pressure of light and the solar environment. In another corner of science, researchers use tightly focused laser beams as optical tweezers. These beams can hold, move, and manipulate tiny particles, droplets, cells, or molecules, not with a physical clamp, but with light itself. A carefully shaped beam creates forces that pull microscopic objects toward the brightest region, allowing scientists to study delicate biological structures without grabbing them with a solid tool. This is one of the places where the idea becomes almost unbelievable. Light, something you usually associate with seeing, becomes a hand. A very gentle hand, but a hand nonetheless. And that changes the way you think about illumination. Light is not just a messenger that lets your eyes know what is there. It is an actor in the world. It can warm, push, bend, scatter, excite atoms, trigger chemistry, and carry information across empty space. It is quiet only because your senses are not built to notice all of its roles at once. The deeper lesson is that touch is not always what it seems. You think of touch as contact between surfaces, skin against glass, hand against table, foot against floor. But at the physical level, forces can cross empty space. Gravity pulls without contact. Magnetism acts without contact, and light too can transfer momentum across distance. The universe is full of invisible exchanges, and what feels like emptiness is often a place where influence is moving. A beam of sunlight crossing a room may look still, but it is a stream of energy, carrying tiny pushes into whatever absorbs or reflects it. Most of the time, matter barely reacts, but under the right conditions, that gentle pressure becomes measurable, useful, even powerful. This is why the phrase, "light can push objects," feels like a doorway into a more subtle reality. It reminds you that the world is not divided neatly into solid things that act and invisible things that merely decorate the scene. The invisible can act. The soft can move the hard. The weightless can still leave a trace. And once you understand that, sunlight no longer seems passive. It becomes a force spread across space, soft enough to fall on your face without pain, yet real enough to move dust around stars and help carry machines through the dark. So the next time you see a beam of light coming through a window, try not to see it only as brightness. See it as motion arriving from far away. See it as the sun, quietly sending pressure across millions of kilometers, touching the room without a hand, touching your skin without a surface, reminding you that even the gentlest things in the universe can shape reality when they are patient enough. Sound can shape sand into patterns. If sound were visible, it would not look like a straight line traveling through the air, but like an invisible sculptor pressing rhythm into matter. You hear a tone and think of it as something that enters the ear, something temporary, something that vanishes the moment the room becomes quiet again. But sound is not only heard. Sound is motion. It is a wave of pressure moving through air, water, metal, glass, wood, and even your own body, making tiny pushes and pulls as it travels. Most of the time, those movements are too small for your eyes to notice. A table does not seem to tremble when someone speaks near it. A window may look still while music fills the room, but under the right conditions, sound can reveal itself by organizing small grains of sand into beautiful patterns, as if the surface beneath them has suddenly remembered a hidden geometry. This is the world of Chladni patterns, named after Ernst Chladni, an 18th century scientist and musician who showed that vibration could turn sound into visible form. The classic experiment is simple, almost hypnotic. A thin metal plate is sprinkled with fine sand. Then the plate is made to vibrate, sometimes with a violin bow drawn along its edge, sometimes with a speaker or vibration generator. At first, the sand jumps and scatters. It looks chaotic, like dust disturbed by an unseen hand. But then, as the vibration settles into a particular tone, the grains begin to travel across the plate and gather into lines. Circles appear, star-like shapes appear, webs, diamonds, crosses, and delicate curves emerge from noise. The sound has not painted the sand directly. It has made the plate vibrate in a structured way. Some parts of the plate move strongly up and down, shaking the sand away. Other parts barely move at all. Those stiller regions are called nodes, and the sand collects there because they are the calmest places on a moving surface. So the pattern you see is not random decoration. It is a map of stillness inside vibration. It shows you where the surface is moving least while the rest of the plate is trembling around it. That is what makes the effect so quietly powerful. Sound does not create order by being loud. It creates order by arranging motion and stillness together. When the frequency changes, the pattern changes too. A low tone may create a simple shape, while a higher tone may divide the plate into more complex regions, because the surface has to fit more waves into the same space. The plate's shape matters. A square plate will not behave exactly like a circular one. Its thickness matters. Its material matters. Where it is held matters. Even the type of sand or powder matters, because lighter grains move more easily than heavier ones. This means the pattern is not a mystical universal symbol floating behind reality. It is the result of real physical conditions. That truth is more fascinating than exaggeration, because it shows how deeply form and motion are connected. The plate is not choosing an image. It is responding to vibration according to its structure. The sound gives energy, the material answers, and the sand becomes the visible record of that answer. You can think of it like listening to a musical instrument with your eyes. A violin string, a drumhead, a guitar body, a bell, or a singing bowl all have certain ways they prefer to vibrate. These preferred vibrations shape the sound they produce. That is why two instruments can play the same note and still feel different. They are not only producing a frequency, they are producing a whole family of vibrations shaped by wood, metal, tension, air, and design. Chladni patterns let you see a similar idea on a flat surface. They show that sound is not separate from matter. It is matter moving in patterns. And once you understand that, the ordinary act of hearing becomes stranger. Every voice that reaches you is a moving disturbance in the air. Every note in a song is a temporary architecture of pressure. Every vibration that enters a room interacts with the surfaces inside it, reflecting, mixing, weakening, strengthening, and sometimes settling into patterns too subtle to see. This is why concert halls are designed with such care. The shape of a room can make sound bloom warmly or disappear into dullness. A badly shaped space can create echoes, dead zones, or harsh spots where certain tones become too strong. A well-designed one guides vibration so that music feels alive. The same principle, in a quieter form, is hiding in the sand on the plate. Space and material decide how sound becomes experience. But there is also something deeply human in watching sand arrange itself under a tone. It reminds you that chaos is sometimes only motion before it has found its pattern. At first, the grains leap without meaning. Then a stable vibration appears, and suddenly they gather into order. Not because someone commanded them grain by grain, but because the conditions made certain places calmer than others. You can watch it happen and feel a strange shift in your own thinking. Maybe order is not always imposed from above. Maybe sometimes it emerges when energy moves through a system in the right way. Maybe the hidden shape was not drawn into the sand, but revealed by movement. That is what makes this experiment so beautiful for a calm science journey. It does not ask you to believe in magic. It asks you to look more carefully at vibration, resonance, material, and pattern. It teaches that sound is not an empty event. It has structure. It can be measured, shaped, reflected, absorbed, and transformed into visible geometry. And it also teaches humility, because something as familiar as a tone can contain more than the ear alone can hold. You may hear a note and think it is only a note, but on a vibrating plate, that same note becomes a landscape. It becomes rivers of sand moving away from unrest and gathering along quiet borders. It becomes proof that the world is full of hidden diagrams, waiting for the right conditions to appear. So the next time you hear music through a wall, a glass humming on a table, or your own voice filling a small room, remember that sound is not just passing through emptiness. It is touching the world in waves. It is asking surfaces how they are built. It is testing the secret habits of matter. And if the conditions are just right, even a handful of sand can answer back, arranging itself into a silent picture of the sound you could not see. A magnet can make metal fall, slowly without touching it. Drop a strong magnet through a copper pipe, and for a moment gravity seems to lose its confidence. The magnet should fall quickly, the way any heavy object falls when you let go. But instead it drifts downward with an eerie smoothness, as if the empty space inside the pipe has thickened into invisible syrup. Nothing is touching it. No hand slows it. No cushion catches it. The copper pipe does not even attract the magnet in the ordinary way, because copper is not like iron. It is not a material that strongly sticks to magnets. And yet the magnet falls slowly, calmly, almost impossibly, as if the metal around it has found a silent way to resist motion without ever making contact. This is one of the most beautiful everyday demonstrations of electromagnetism, because it reveals that metal is not just a solid object sitting there. Inside a conductor like copper or aluminum, there are electrons that can move, and when a magnet moves near them, it can disturb them into motion. As the magnet falls through the pipe, its magnetic field passes through the copper walls. That changing magnetic field nudges electrons in the copper into circular currents, known as eddy currents. You can imagine them as tiny loops of electrical motion swirling in the metal, not because a battery has been connected, but because the falling magnet itself has created the conditions for electricity to appear. But here is where the deeper rule of nature enters. Those induced currents do not simply appear passively. They create their own magnetic fields, and those magnetic fields oppose the change that caused them. This is often called Lenz's law, and it is one of those simple ideas that feels almost philosophical once you understand it. Nature resists sudden change, not emotionally, not intentionally, but physically. When the magnet moves downward, the currents in the pipe generate a magnetic response that pushes back against that motion. Above the magnet, the induced effect can act in a way that pulls upward. Below it, it can act in a way that resists the magnet's approach. The result is not a complete stop, because gravity is still pulling the magnet down, but a slow fall, a controlled descent, a quiet tug of war between gravity and induced magnetism. The magnet is not floating by magic. It is constantly losing gravitational energy, but instead of becoming speed, much of that energy becomes tiny amounts of heat in the copper as electrical currents flow through resistance. The pipe may warm by an extremely small amount, usually too little for your hand to notice, but the energy has gone somewhere. It has been transformed. This is why the demonstration matters. It teaches that slowing down is not disappearance. Motion does not simply vanish. Energy changes form, moving from falling movement into electrical motion and then into heat. And this same idea is not just a classroom trick. It appears in real machines. Some trains and roller coasters use magnetic braking, where moving conductors and magnets create eddy currents that slow motion smoothly without relying on friction pads rubbing together in the usual way. Some exercise bikes, industrial systems, and measuring instruments use similar principles to produce resistance or damping. Because the braking comes from motion itself, it can be incredibly smooth. The faster the conductor moves through the magnetic field, the stronger the induced currents tend to be, and the stronger the opposing effect becomes. That is why the magnet in the pipe does not crash downward at full speed. As it tries to speed up, the magnetic resistance grows until it reaches a steady, slower fall. It is almost as if the system finds a compromise. Gravity says go faster, the induced currents say not so fast, and the magnet descends at a quiet pace between the two. But it is important to be precise. This does not happen with every metal in the same way. If you drop a magnet through a plastic tube, nothing similar happens because plastic does not allow the same kind of free electron motion. If you drop it near iron, the situation becomes different, because iron can be strongly attracted to the magnet, and may stick or pull sideways. Copper and aluminum are especially good for this kind of demonstration because they conduct electricity well while not strongly attracting the magnet. The effect also depends on the strength of the magnet, the thickness and conductivity of the metal, the shape of the object, and how quickly the magnetic field changes. A weak refrigerator magnet may not create a dramatic slow fall, but a strong neodymium magnet inside a thick copper tube can look astonishing, as if the pipe has become a tunnel of invisible resistance. What makes it so fascinating is that the copper seems ordinary until the magnet moves. If the magnet is held still inside the pipe, there is no dramatic braking force of the same kind, because the magnetic field is no longer changing through the copper. The secret is not just magnetism, it is changing magnetism. Motion wakes the effect up. Stillness lets it sleep. That small difference opens a door into much of modern electrical technology, because generators also work by using motion and changing magnetic fields to create electric currents. In a power station, spinning parts and magnetic fields are arranged so that mechanical motion becomes electricity. In the falling magnet demonstration, the same family of principles appears in miniature. You are watching gravity try to turn motion into speed, while electromagnetism quietly redirects part of that energy into circulating currents. It is a tiny power station with nowhere useful to send the power except into warmth. And there is something strangely calming about this, because the falling magnet reveals a kind of hidden conversation inside matter. You see only a shiny pipe and a small object descending through it, but beneath that simple scene is an invisible architecture of fields, currents, resistance, energy transfer, and balance. The metal is not alive, but it responds. The magnet is not thinking, but it provokes. The space between them is not empty in the everyday sense, because fields are passing through it, changing it, shaping what motion is allowed to become. This is the kind of physics that makes the ordinary world feel less solid and more relational. Objects are not isolated things bumping into each other only when they touch. They influence, disturb, resist, and answer one another through invisible structures. A magnet can fall slowly through copper, not because gravity has weakened, but because another force has entered the story. One that awakens only through motion and expresses itself without contact. And maybe that is the quiet lesson hiding inside the demonstration. Some resistance is invisible. Some forces do not announce themselves until something moves. Some systems only reveal their deeper rules when change begins. You can hold the copper pipe in your hand, and it seems like nothing special, just metal, just a tube, just a simple object. But let the magnet fall, and suddenly the pipe becomes a teacher. It shows you that the world is full of hidden responses, that empty space can be crossed by fields, that matter can answer motion with motion of its own, and that even a falling object can become a lesson in how nature protects balance. So when the magnet drifts downward slower than it should, do not see it as a violation of common sense. See it as common sense expanding. See it as gravity meeting electromagnetism in a silent hallway. See it as proof that the unseen is not unreal. Sometimes the most powerful part of the world is not the thing you can touch, but the quiet force that changes what touching even means. Water can climb up, thin tubes against gravity. A thin glass tube dipped into water can look like it is quietly disobeying the planet. You expect water to fall downward, to spread outward, to surrender to gravity the way every spilled drink does. But inside a narrow tube, something stranger happens. The water rises. It climbs upward by itself, not because a pump is pulling it, not because heat is lifting it, not because some hidden machine is forcing it, but because the water and the tube are interacting at a scale your eyes usually ignore. This is called capillary action, and it is one of those everyday physics effects that feels small until you realize how much of life depends on it. The secret begins at the surface, where water touches another material. Water molecules are attracted to each other, which helps them stay together as a liquid, but they can also be attracted to other surfaces, especially surfaces like clean glass, paper fibers, cloth, soil particles, or the tiny inner walls of plant vessels. When water is more attracted to the wall of a thin tube than it is pulled back into its own body, it begins to creep upward along that wall. The water touching the surface climbs first, and because water molecules also cling to one another, they pull neighboring molecules along with them. It is not one molecule escaping alone. It is a chain of attraction, a quiet upward cooperation between the surface and the liquid. This is why the tube must be thin. In a wide container, the upward pull along the edges is too small compared with the weight of all the water in the middle, so you barely notice it. But in a very narrow space, the surface becomes more important. There is less water to lift, and more of it is close to the wall. The smaller the tube, the more powerful the effect can appear because the liquid is surrounded more completely by the surface that pulls on it. If you look closely at water in a glass tube, the top surface is not perfectly flat. It curves upward at the edges, forming what is called a concave meniscus. That curve shape is a clue. It shows that the water is reaching toward the glass, almost like a tiny transparent hand holding the wall. The rise stops only when the upward pull from the surface is balanced by the weight of the water column. Gravity has not been defeated. It has been negotiated with. Water climbs only until the forces reach a calm agreement, and then it rests there, suspended higher than you expected, held by attractions too small to feel and too important to ignore. You can see the same principle whenever a paper towel drinks up a spill. The towel does not suck water in the way a mouth sucks through a straw. Instead, its fibers create countless tiny channels, and water climbs through them by capillary action. That is why a corner of a dry napkin can touch a puddle and slowly darken far beyond the point of contact. The water is traveling through narrow spaces, pulled along fiber by fiber. The same thing happens in cotton, in paintbrush bristles, in chalk, in sponges, in the wick of a candle or oil lamp. A wick works because liquid fuel climbs upward through thin fibers to reach the flame, where it can burn. Without capillary action, that small, steady feeding of liquid would be much harder. Even the ground beneath your feet uses this effect. In soil, water can move through tiny gaps between grains, helping moisture spread through the earth. In some places, capillary action can draw groundwater upward toward plant roots. In others, it can pull dissolved minerals toward the surface as water evaporates, leaving pale crusts of salt behind. What looks like dirt is actually a maze of microscopic passageways, and water moves through that maze according to the same quiet rules that lift it inside a glass tube. But perhaps the most meaningful example is inside plants. A tall tree does not have a mechanical pump, like a heart pushing water from the roots to the leaves. Its water transport is more complex than capillary action alone, because evaporation from leaves and the cohesion of water molecules play a major role, creating a pull through the plant's xylem. But capillary action helps water interact with the tiny tubes and surfaces inside plant tissues, supporting the movement of liquid through narrow pathways. When you look at a tree, you are looking at a living tower that depends on water's ability to cling, pull, rise, and remain connected in thin channels. The leaves above you are not just decorations. They are part of a continuous water system stretching from the soil into the air. Water enters through roots, travels through narrow vessels, and eventually escapes from leaves as vapor, helping draw more water upward. The whole process is delicate, physical, and astonishingly efficient. A forest, in this sense, is not only a collection of trunks and branches. It is a vertical river system, lifted by forces too subtle to see directly. And there is a beautiful lesson in how selective this effect is. Water rises in clean glass because it is strongly attracted to the glass surface. But not every liquid behaves the same way with every material. Mercury, for example, tends to pull more strongly toward itself than toward glass. So in a glass tube, it forms a rounded surface that curves downward at the edges and may not climb the way water does. That contrast matters because it shows that capillary action is not a magical property of tubes. It is a relationship. The liquid, the surface, the narrowness of the space, and the pull of gravity all decide what happens together. Change one part of the relationship, and the behavior changes. This is why everyday physics is so rich. The world is not made only of things, but but of interactions between things. Water in an open bowl behaves one way. Water in a hair-thin tube behaves another. Water on wax beads up differently than water on glass. Water in paper spreads, while water on oily plastic may refuse to soak in. The same liquid can seem obedient, restless, climbing, spreading, or resisting, depending on what it touches. And when you understand that, you begin to see surfaces differently. A wall is not just a boundary. A fiber is not just a thread. A pore is not just an empty gap. Each one can guide matter, invite it, reject it, slow it, lift it, or reshape its path. Capillary action is not loud. It does not announce itself with sparks or dramatic movement. It is slow, patient, and almost silent, but it is everywhere. It helps ink flow through paper, helps towels absorb water, helps plants live, helps small channels carry fluids in laboratories, and helps natural materials manage moisture in ways that human engineering often tries to copy. It reminds you that small forces can become powerful when the space is small enough, and that scale changes everything. What looks weak in a large room can become decisive in a narrow passage. What seems impossible in the open can become natural in a hidden channel. So the next time you see water creeping up the edge of a straw, soaking through a napkin, darkening the bottom of a plant pot, or spreading through a strip of paper, do not think of it as a minor detail. See it as a quiet rebellion made of attraction and balance. See it as water revealing that gravity is not the only author of motion. The world is full of tiny upward paths, tiny invitations, tiny surfaces saying come closer, and water answering molecule by molecule. And perhaps that is why capillary action feels so strangely comforting. It shows that rising does not always require force. Sometimes it happens through closeness, through connection, through the patient pull between one thing and another, until what should have stayed low begins, gently and truthfully, to climb. A liquid can behave like a solid when hit. Hit a bowl of cornstarch and water hard enough, and the liquid seems to forget that it is supposed to flow. One moment it drips between your fingers like thick cream, soft, messy, and obedient to gravity. The next moment, under a sudden punch or fast squeeze, it stiffens beneath your hand like a surface with memory, as if the liquid has briefly locked itself into a hidden solid. This is not magic, and it is not a trick of perception. It is a real behavior found in certain materials called non-Newtonian fluids, where the thickness of the fluid changes depending on how it is forced to move. Ordinary water behaves in a much simpler way. Stir it gently or stir it quickly, and although the motion changes, the water itself does not suddenly become dramatically thicker. But a mixture like cornstarch and water is different because it is not just a liquid. It is a suspension, meaning tiny solid particles are packed inside a liquid, floating, sliding, and shifting past one another. When you move slowly, those particles have time to rearrange. They can slip around each other and the mixture flows. You can sink your fingers into it if you press gently. You can let it pour, although it pours strangely. But when you strike it quickly, the particles do not have enough time to move out of the way. They crowd together, press into one another, and form a temporary jammed structure. For a brief moment, the mixture becomes resistant, not because it has truly turned into a permanent solid, but because the particles have locked into a force-bearing network that can push back. The liquid between them is still there, but it cannot help them slide smoothly when the pressure arrives too suddenly. This is called shear thickening, and it teaches you something quietly powerful. A material is not always defined only by what it is made of, but by how you interact with it. Touch it softly, and it behaves one way. Strike it sharply, and it behaves another. The same substance can feel gentle or stubborn, depending on the speed of your hand. That is why people can sometimes run across a pool filled with a cornstarch water mixture, as long as they keep moving quickly and the mixture is prepared correctly. Each fast step creates a jammed region beneath the foot, a temporary support strong enough to resist for a moment. But if the person stops, the pressure becomes slow rather than sudden. The particles have time to rearrange again, and the body sinks. The solid was never a stable floor. It was a momentary agreement between impact, particle crowding, and timing. This is also why trying to stir such a mixture quickly can feel almost impossible, while slowly pushing the spoon through it works. The material is not confused. It is responding with remarkable precision to the way force is applied. And this idea reaches beyond a kitchen experiment. Scientists and engineers study shear thickening fluids because they can absorb sudden impacts in useful ways. Some protective materials use similar principles, combining flexible fabrics with fluids or particle-filled systems that remain soft during normal movement but stiffen under rapid force. The dream is elegant. Clothing or protective gear that bends with the body during ordinary motion, yet becomes more resistant when struck. Not all such designs are simple, and not every non-Newtonian fluid works the same way, but the principle is real and deeply useful. It shows that softness and strength do not always have to be opposites. Sometimes strength can appear only when needed. Sometimes protection can hide inside flexibility. What makes this behavior so fascinating is that it challenges the labels you usually trust. You like to divide the world into categories: solid, liquid, gas, hard, soft, stable, flowing. But matter is more subtle than those boxes. A liquid can be liquid under one kind of stress and solid-like under another. Sand can support weight when packed but flow when poured. Foam can hold shape and collapse. Mud can swallow a boot but crack when dry. The physical world is full of materials that live between categories, and non-Newtonian fluids make that in-between nature visible in your own hands. They remind you that matter is not always a fixed identity. Sometimes it is a behavior, a response, a relationship between structure and force. In the case of cornstarch and water, the tiny particles are like a crowded room of people. If everyone moves slowly, they can pass one another politely. But if a sudden rush pushes through the crowd, bodies press together, paths vanish, and the whole crowd locks in place. That is not because the people changed into a wall. It is because the timing and pressure changed how they could move. The particles in the mixture do something similar. Given time, they flow. Denied time, they jam. And when you see that happen, when your hand bounces off something that was dripping a second earlier, you are watching a hidden rule of matter become visible. Motion can change material identity. The lesson is not that liquids secretly want to be solids. The lesson is that the boundary between liquid and solid is not always as clean as it feels in daily life. In the right systems, under the right conditions, matter can switch its behavior almost instantly, revealing that soft and hard are not permanent truths, but possible states. So the next time you see a simple bowl of cornstarch and water, do not see it as a children's experiment or a messy kitchen curiosity. See it as a small doorway into the science of complex materials. See it as proof that the ordinary world has rules that only appear when you disturb it in the right way. Press gently and it welcomes you. Strike quickly and it resists. Wait and it relaxes again. There is something almost meditative in that rhythm. The world answering not only to what you do, but to how suddenly you do it. And maybe that is why this strange liquid stays in the memory. It teaches with your fingertips. It lets you feel that reality is not always one thing at a time. Sometimes it flows when approached with patience, stiffens when met with force, and reveals in a single surprising touch that even the simplest materials may be holding more than one nature inside them. Some materials remember their original shape. Bend a piece of special metal until it looks ruined. Warm it gently, and it may begin to unfold itself like it has remembered who it used to be. At first, this feels almost impossible because most objects do not forgive deformation so easily. If you crush a soda can, it stays crushed. If you bend a paperclip too far, it weakens or snaps. If you dent a soft piece of metal, the dent usually remains like a small scar in the material. But some materials behave differently. They can be twisted, bent, stretched, or compressed. And then, when the right condition returns, they move back toward a previous shape, as if that shape was stored somewhere inside them. These are called shape memory materials, and the most famous examples are shape memory alloys, especially a nickel-titanium alloy known as nitinol. The secret is not memory in the human sense. The metal is not thinking, choosing, or recalling an image. Its memory lives in the arrangement of its atoms and in the way that arrangement changes with temperature or force. Deep inside the material, atoms are organized in patterns, and in shape memory alloys, those patterns can shift between two different internal structures. One structure is more stable at lower temperatures and can be bent more easily. The other is more stable at higher temperatures and carries the original trained shape. When the metal is cool, you can deform it because the internal structure can rearrange in a flexible way. But when you heat it past a certain point, the atoms shift back into the warmer structure, and that shift pulls the entire object back toward the form it was trained to hold. The movement can look alive. A bent wire straightens, a folded loop opens, a twisted shape relaxes back into a clean curve. But what you are really seeing is a phase change inside a solid, not from solid to liquid, but from one solid atomic arrangement to another. This is what makes the effect so fascinating. The material does not melt, flow, or soften like wax. It remains solid while its inner architecture reorganizes, and that hidden reorganization becomes visible as motion. Nitinol is especially useful because it can survive this kind of transformation many times when designed properly, which makes it valuable in medicine, engineering, robotics, and small devices where controlled movement is needed without motors. One of the most important uses is in medical stents, tiny tube-like supports that can be compressed into a small shape, inserted into the body, and then expand when they reach warmer body temperature. In that case, the material's response is not just a laboratory curiosity, it can help open blood vessels and support life. Shape memory alloys can also appear in flexible eyeglass frames that bend and return, in dental wires that apply steady, gentle force, in temperature-sensitive actuators that open vents or valves, and in devices where a small change in heat creates mechanical motion. There is another related behavior called superelasticity, where some shape memory alloys can stretch or bend dramatically and return to their original form even without being heated, as long as they are used within the right temperature range. In that case, force itself triggers a temporary internal shift, and when the force is removed, the material springs back. This is why some nitinol frames can seem strangely resilient, bending much farther than ordinary metal without staying bent. But it is important to stay honest about the limits. Shape memory materials do not repair every kind of damage. If you bend them too far, overheat them, crack them, fatigue them through too many cycles, or use them outside their designed range, they can fail like anything else. Their memory is not infinite. It is a carefully engineered behavior dependent on composition, temperature, processing, and training. Even the word training has a specific meaning here. Engineers can heat treat the alloy in a desired shape so that its high temperature structure favors returning to that form. In other words, the material is not born remembering any shape you imagine. Its memory is built into it through manufacturing. That makes the effect even more meaningful, because it shows how deeply the properties of matter depend on structure. Two pieces of metal may look similar from the outside, but if their atoms are arranged differently, or if they were processed differently, they can behave like entirely different worlds. One stays bent, another returns. One breaks, another transforms. This idea also extends beyond metals. Some polymers can have shape memory behavior too. They may be deformed into a temporary shape and later return when heated, exposed to light, moisture, or another trigger, depending on how they are designed. Researchers explore these materials for soft robotics, smart textiles, medical tools, self-deploying structures, and objects that can change form when their environment changes. A future device might fold small, travel through a narrow space, then open itself when warmed. A fabric might adjust ventilation. A soft machine might move without hard gears, using material behavior as part of the mechanism. That is the larger lesson. Sometimes the intelligence of a system is not in a computer chip or a motor, but in the material itself. Matter can be designed so that its response is built into its body. It can become an instruction written in structure, and this makes you look at ordinary objects differently. A spoon, a wire, a frame, a spring. a thread, a sheet of plastic. All of them may seem passive, but their behavior is the result of hidden architecture. Every material carries a kind of physical personality. How it bends, how it breaks, how it stores energy, how it reacts to heat, how it returns or refuses to return. Shape memory materials make that personality dramatic enough to see. They remind you that form is not always final. Sometimes a distorted shape is only temporary because the deeper structure is waiting for the right signal to reappear. And there is something quietly reflective in that. A material can be bent out of shape and still hold within its hidden order a path back. Not because it is magical, not because it has a soul, but because its inner structure was prepared to transform. Science does not need exaggeration here. The real phenomenon is already beautiful. A wire remembering a curve, a stent opening in warmth, a frame bending and returning, a polymer unfolding when triggered. These are reminders that the physical world is not as rigid as it first appears. Some things can change without losing themselves. Some structures can absorb disturbance and come back. Some forms are not erased by pressure, only hidden until the right conditions return. So when you see a shape memory alloy straighten in warm water, or a flexible frame spring back after bending, do not see only a clever material trick. See a quiet message written in atoms. Memory can exist as structure, motion can be stored as possibility, and even solid matter can carry a past shape inside it, waiting patiently for warmth to call it home. A drop of water can hover on a hot pan. A single drop of water on a hot pan can begin to dance as if it has found a way to float above danger. You expect it to vanish instantly, to hiss once and disappear into steam, and on a moderately hot surface, that is often what happens. The drop touches the metal, spreads out, boils violently, and evaporates quickly. But heat the pan far beyond boiling temperature, and something stranger appears. Instead of dying faster, the drop may survive longer. It beads up into a trembling little sphere, skitters across the surface, and hovers on a cushion of its own vapor. This is called the Leidenfrost effect, and it is one of those rare everyday phenomena where the world seems to contradict common sense while obeying physics perfectly. The secret is not that the water has become immune to heat. The secret is that the bottom of the drop evaporates so rapidly that it creates a thin layer of steam between the liquid and the pan. That vapor layer acts like a temporary shield. It separates the drop from direct contact with the metal, and because steam does not transfer heat as efficiently as solid metal does, the drop receives heat more slowly than it would if it were touching the pan completely. So the drop survives, not by resisting heat, but by riding on the first part of itself that has already turned into gas. It is almost like the water builds a tiny escape platform from its own evaporation. This is why the effect only happens above a certain surface temperature. If the pan is not hot enough, the vapor layer cannot form strongly and continuously, so the water touches the surface and boils away quickly. If the pan is hot enough, the steam forms so fast that it lifts the drop slightly, reducing contact and letting it glide. The drop then becomes mobile because it is no longer pinned flat to the surface. It can slide, spin, bounce, and race across tiny imperfections in the pan, pushed by uneven vapor flow beneath it. Sometimes it looks playful, but the physics is serious. The drop is balanced between gravity pulling it down, vapor pressure pushing it up, surface tension holding it together, and heat constantly trying to transform it into steam. Inside that small shimmering bead, the water is not calm. Its lower surface is boiling, its outer shape is vibrating, its edges are losing mass, and its path across the pan is shaped by invisible jets of vapor. What looks like a tiny floating pearl is actually a miniature heat engine, converting thermal energy into motion. This same effect can happen with other liquids too, not only water, depending on their boiling points and the temperature of the surface. It also matters what the surface is made of, how rough it is, how clean it is, and how well it conducts heat. A smooth metal surface can let the drop glide easily, while a rough or textured surface may interrupt the vapor cushion and make the behavior less stable. Scientists study this effect not just because it is beautiful, but because it matters in cooling systems. engines, industrial processes, and safety. When a very hot surface needs to be cooled, you might assume pouring liquid onto it would always help. But the Leidenfrost effect can actually reduce cooling efficiency by keeping the liquid from touching the surface directly. The vapor layer becomes an insulating barrier, slowing heat transfer at the very moment you want heat to escape quickly. This is important in situations involving overheated metals, nuclear reactors, high-temperature manufacturing, firefighting, and any system where liquid cooling meets extreme heat. In other words, the dancing drop on a kitchen pan is not just a curiosity. It is a small, visible version of a problem engineers take seriously. Sometimes, the hotter something gets, the harder it becomes to cool it in the simplest way. There is also a strange lesson in timing. Below the Leidenfrost point, water dies quickly on the pan because it makes full contact. Above it, water survives longer because it is separated by vapor. But if the temperature is extreme enough, the drop will still eventually disappear. The effect delays evaporation. It does not cancel it. The drop is always being consumed from below, always spending itself to stay lifted. Its protection is temporary, made from loss. And perhaps that is why the phenomenon feels so memorable. It shows that survival is not always about hardness or resistance. Sometimes it is about creating distance at exactly the right boundary. The water is fragile, yet for a little while, it turns the danger beneath it into a cushion. The same heat that threatens to destroy it also creates the vapor layer that keeps it alive. That is not a contradiction. It is balance. It is the world revealing that cause and effect can fold into each other in subtle ways. The pan does not simply burn the drop away. It gives the drop a new state of motion before it disappears. And once you have seen this, a hot surface no longer feels like a simple place of destruction. It becomes a stage where liquid, gas, heat, and motion negotiate moment by moment. A single water drop becomes a lesson in phase change, insulation, pressure, and instability. It teaches you that boiling is not just one event, but many possible behaviors depending on contact. It teaches you that heat can create barriers as well as break them. It teaches you that the boundary between water and steam is not passive. It can lift, slide, and reshape motion. So the next time you sprinkle water onto a hot pan and watch the droplets scatter like tiny living things, do not see only a cooking test. See a quiet physical trick performed in plain sight. See liquid hovering on the ghost of itself. See a small body protected by the vapor it becomes. And let it remind you that the ordinary world is filled with thresholds. Cross one temperature and boiling becomes violent. Cross another and the same water begins to float. Reality often changes not because the substance has changed, but because the conditions around it have crossed a hidden line. In that moment, a drop does not merely sit on a pan. It dances on the edge between liquid and air, between contact and separation, between disappearance and delay, showing you that even the simplest kitchen sound, a hiss, a skitter, a tiny bead racing across metal, can contain a whole secret physics of survival. Bubbles solve geometry problems automatically. A bubble does not know mathematics, yet the moment it forms, it begins solving a problem that can challenge the human mind. You blow gently through a wand. A thin film stretches into the air, and suddenly a sphere appears, trembling in the light, fragile enough to vanish from a finger touch and clever enough to arrange itself into one of nature's most efficient shapes. It looks playful, almost childish, the kind of thing you chase in sunlight without thinking too deeply about it. But hidden inside that floating skin is a quiet rule. Bubbles tend to find shapes that use the least surface area for the space they enclose. They are not thinking, calculating, or choosing. They are obeying physical forces. A soap film is made from a very thin layer of water held between soap molecules, and that film has surface tension, a kind of natural pull that tries to shrink the surface as much as possible. If a bubble encloses air, the film pulls inward from every direction, and the shape that balances that pull most evenly is a sphere. That is why a free-floating bubble becomes round. A cube-shaped bubble would have corners and edges that create uneven tension, and the film would quickly smooth them away. A sphere is not just pretty, it is efficient. It holds volume with the smallest possible surface, so the bubble becomes a tiny lesson in economy, as if nature is whispering, do the most with the least. But the real wonder begins when bubbles meet other bubbles. One bubble alone becomes a sphere, but a cluster of bubbles becomes a living geometry problem. They press against each other, flatten where they touch, curve where pressure differs, and arrange their shared walls in ways that minimize total surface area. If several bubbles of equal size meet, their films often join at angles close to 120 degrees, because that is the stable balance point where the pulls of the films can cancel evenly. You may not notice this while washing dishes or watching foam gather in a sink, but if you look closely, soap bubbles are constantly organizing themselves into efficient networks. They do not waste film where less will do. They share walls instead of building separate boundaries. They adjust their curves depending on pressure. A small bubble has a higher internal pressure than a larger one, so when bubbles of different sizes touch, the wall between them can curve toward the larger bubble. This is not decoration. It is pressure made visible. The bubble is showing you how invisible forces negotiate space. And this is why scientists, mathematicians, architects, and engineers have long been fascinated by soap films. Dip a wire frame into soapy water and pull it out, and the film that forms across it often reveals a minimal surface, the smallest area surface that can span that frame. The film finds it automatically because any extra area costs energy. It relaxes into the most efficient shape available under the conditions. Human beings can spend pages working out these shapes, while the soap film arrives there almost instantly, not by intelligence but by physical necessity. In this sense, a bubble becomes a natural computer, not electronic, not conscious, but capable of finding solutions through the way matter settles into lower energy. This principle appears far beyond soap. Foams in bread, shaving cream, sea foam, beer, insulation materials, and even some biological tissues all involve bubbles or bubble-like structures packing together, sharing walls and trying to reduce energy. The geometry of foam helps explain why certain repeated shapes appear so often in nature. Cells in some tissues can look like packed bubbles because each cell is pressed among neighbors, and their boundaries can arrange into efficient patterns. Honeycomb structures are different in origin, built by bees rather than soap films, but they also reveal nature's attraction to efficient packing, a pattern that uses material carefully while filling space strongly. In foam, however, the efficiency emerges directly from surface tension and pressure. The bubbles are not building a plan. The plan is what remains after unstable possibilities disappear. This is what makes them so beautiful to watch. They teach without speaking that form can arise from constraint. The bubble cannot become anything it wants. It must obey tension, pressure, gravity, liquid thickness, drainage, evaporation, and the pull of nearby surfaces. Yet within those limits it finds elegance. It becomes round, then shared, then clustered, then foam, each stage revealing a new level of hidden order. Even the life and death of a bubble has physics inside it. Over time, liquid drains downward through the film, making the top thinner. Water evaporates. The soap layer becomes fragile. Colors ripple across the surface because different film thicknesses reflect light differently, turning the bubble into a shifting map of its own thinning skin. When it finally pops, it is not simply gone. The film has become too thin to hold the pressure and tension together, and the structure collapses faster than your eye can fully follow. For a moment, geometry exists. Then the conditions fail, and the shape vanishes. There is something deeply reflective in that. A bubble is temporary, but while it exists, it is precise. It is delicate, but not random. It is playful, but not meaningless. It solves geometry, not because it understands geometry, but because the universe often solves by relaxing, by balancing, by removing excess until only the most stable shape remains. And perhaps that is why bubbles feel strangely calming even when they are fragile. They remind you that beauty does not always need permanence. Sometimes beauty is a correct answer held for a few seconds in the air. Sometimes intelligence is not a mind but a process. Sometimes the world finds order not by force, but by letting tensions settle into balance. So the next time you see foam on coffee, bubbles in a sink, sea foam at the edge of a wave, or a single soap bubble drifting in sunlight, do not see only something childish or empty. See a surface trying to become as small as it can while holding a world inside it. See invisible pressure bending a wall. See films meeting at careful angles. See nature solving a quiet geometry problem in real time, using nothing more than air, water, soap, and the ancient desire of matter to spend as little energy as possible. And maybe let that small, transparent sphere ask you something gentle. How much of the order around you has been hiding in plain sight, waiting for you to stop calling it ordinary? A laser can cool atoms almost to absolute zero. A laser usually feels like a symbol of heat, danger, and cutting power, yet in the quietest laboratories on Earth, carefully tuned laser light can make atoms slow down until they become almost perfectly still. That sounds backward at first, because you imagine a laser as something that burns through metal, points sharply through fog, or concentrates energy into a bright, intense beam. But temperature, at the atomic level, is not just about how hot something feels to your hand. Temperature is closely tied to motion. In a gas, atoms are constantly flying around, colliding, bouncing, and racing in all directions. The hotter the gas, the faster that restless motion becomes. So if you want to cool atoms, you are really trying to slow them down. You are trying to calm the invisible storm. And this is where laser cooling becomes one of the most elegant tricks in modern physics. Scientists use light not to heat atoms, but to gently take away their motion, one tiny push at a time. The idea begins with the fact that atoms can absorb very specific colors of light. Not any color, not any random beam, but light whose energy matches a transition inside the atom. If the laser is tuned just slightly below the color the atom naturally absorbs, something strange and useful happens. An atom moving toward the laser sees the light shifted slightly, almost as if the color has changed from the atom's point of view. Because of that motion, the laser light becomes closer to the color the atom wants to absorb. The atom takes in a photon from the beam, and that photon gives it a tiny push opposite its movement. One push is unimaginably small. But repeat this again and again across millions of atoms, with laser beams coming from different directions, and the atoms begin to slow. It is like trying to calm a swarm of invisible bees by sending tiny, perfectly timed taps against every bee that moves too fast. The laser does not grab the atom, it does not freeze it in place. It persuades it downward in speed through countless small interactions. After an atom absorbs light, it later releases light again in a random direction. That release gives the atom another little recoil. But because the emissions happen in many directions over time, those random pushes mostly average out. The important repeated push is the one from the laser beam the atom absorbs while moving toward it. With beams arranged from several sides, atoms moving in nearly any direction can be slowed. This creates what scientists sometimes call optical molasses, a beautiful phrase for a real effect. Atoms moving through overlapping laser beams feel a kind of light-based resistance, as if space itself has become thick and gentle around them. They are not stuck, but their motion is damped. They drift more slowly. Their temperature falls to levels far below anything found in ordinary daily life. To hold them in place more effectively, scientists often combine laser cooling with magnetic fields in a device called a magneto-optical trap. In that trap, magnetic fields help make the cooling forces depend on where the atoms are, so the atoms are not only slowed but gathered near the center. You can think of it as a nearly invisible bowl made of light and magnetism. Not a bowl with walls, but a region where atoms are guided back when they wander too far. This matters because atoms at ordinary temperatures move too quickly to study with extreme precision. They blur through experiments. Their motion hides delicate quantum behavior, but when they are cooled to incredibly low temperatures, their wave-like nature becomes easier to observe. Atomic clocks become more precise, and scientists can create exotic states of matter such as Bose-Einstein condensates, where many atoms begin acting less like separate particles and more like one shared quantum system. Still, it is important to say this clearly. Lasers do not reach absolute zero, and absolute zero itself cannot be fully reached by any physical process. Absolute zero is the point where thermal motion is as low as nature allows. But the rules of quantum physics prevent a simple picture of atoms becoming perfectly frozen in every possible way. Laser cooling can bring atoms extremely close, and other techniques can push them even colder, but never all the way to absolute zero. That limit makes the achievement more profound, not less. Scientists are not breaking reality. They are approaching one of its deepest boundaries, and the fact that light can do this should make you rethink what light really is. A laser is not simply brightness. It is controlled interaction. It can cut when intense and absorbed in one way. It can measure when used another way. It can cool when tuned with extraordinary care. The same physical thing that can scorch a surface can also slow an atom, depending on color, direction, timing, and scale. That is the beauty of this topic. It shows that the meaning of a force depends on the world it enters. To your hand, a laser may seem like heat. To a fast-moving atom in a vacuum chamber, the right laser can become a quiet break. And there is something almost meditative in that reversal. The coldest places humans have ever made are not dark caves or frozen mountains, but bright laboratory chambers where beams of light cross like silent threads. Inside them, atoms are slowed so deeply that the ordinary violence of heat fades into near stillness. The room around the experiment may be warm, the equipment may hum, the scientists may walk and speak, but in the center, a tiny cloud of matter is being coaxed into a state of extraordinary calm. It reminds you that cold is not only the absence of warmth. In physics, it can be the slowing of motion, the quieting of chaos, the soft reduction of speed until matter begins to reveal behaviors normally hidden by its own restlessness. So when you hear that a laser can cool atoms almost to absolute zero, do not picture a beam pouring coldness into matter like ice water into a glass. Picture instead a patient conversation between light and motion. Picture photons arriving from carefully chosen directions, meeting atoms that are moving too quickly, nudging them back again and again until their invisible dance becomes slower, softer, more readable, and maybe let that image stay with you. Not all power is loud, not all light burns, and sometimes the deepest cold is made not by darkness, but by brightness disciplined enough to teach matter how to be still. Static electricity can bend water. Bring a charged comb near a thin stream of water, and the stream may lean toward it, like something invisible has called its name. Nothing touches the water, no hand guides it, no wind pushes it. The comb simply comes close, and the falling thread of water curves sideways, gently, almost shyly, as if the liquid has sensed a presence in the air. This small experiment looks simple enough to belong in a classroom or a kitchen sink, but it opens a quiet doorway into one of the most important facts about matter. Even things that look electrically neutral can be influenced by electric charge. To create the effect, you might rub a plastic comb or balloon against dry hair or wool. During that rubbing, tiny charged particles called electrons can move from one material to another. The comb may gain extra electrons and become negatively charged, or another object may lose electrons and become positively charged. Either way, the object is no longer electrically balanced. It now carries a static charge, meaning the charge stays gathered on the surface instead of flowing away immediately like an electric current in a wire. When you bring that charged object near a thin stream of water, the water bends because water molecules are polar. This does not mean the water itself has become charged overall. It means each water molecule has a slightly uneven distribution of electrical charge. One side is a little more negative, and the other side is a little more positive. You can imagine each molecule as a tiny object with two different electrical personalities on opposite ends. When a charged comb approaches, the nearby water molecules rotate and shift their orientation so that the side attracted to the comb faces it more strongly. If the comb is negatively charged, the slightly positive side of many water molecules is drawn toward it. If the comb is positively charged, the slightly negative side turns toward it instead. The important point is that attraction can happen even when the whole water stream is neutral, because the charge inside each molecule is not spread perfectly evenly. The stream bends because the attraction on the closer side is slightly stronger than the repulsion on the farther side, and across countless molecules, that tiny imbalance becomes visible as motion. This is one of those beautiful moments where the hidden structure of matter rises into plain sight. You are not seeing water being scared or water becoming magnetic. You are seeing electric fields acting on polar molecules. The charged object creates an electric field around it, a region where other charges or polar materials can feel a force. The water passes through that region, and the stream curves, because the molecules inside it are being gently pulled into a new arrangement. The effect works best when the stream is very thin, because a thinner stream has less mass and is easier to deflect. It also works better in dry air, because humidity helps static charge leak away from surfaces more quickly. On a damp day, the comb may lose its charge before you can make the water move. This is why static shocks are often stronger in dry winter air. Charges can remain separated longer when the air and surfaces do not conduct them away easily. And this is also why the experiment can fail if the water stream is too thick, the comb is not charged enough, or the room is too humid. The science is real, but the conditions matter. What makes the bending water so memorable is that it challenges your idea of what influence requires. You are used to thinking that something must touch the water to move it. A spoon must stir it, a hand must pour it, a pipe must direct it. But electricity does not need contact to create a force. The charge comb never enters the stream, yet the water responds. This is not because the water is alive, but because the molecules inside it are built with a subtle internal imbalance that makes them sensitive to electric fields. That same polarity is one reason water is so extraordinary in many other ways. It helps water dissolve salts and many other substances. It helps water molecules attract one another. It helps shape the behavior of droplets, biological chemistry, and the environment inside living cells. The tiny electrical unevenness inside water is not a minor detail. It is one of the reasons water can be the medium of life. So when a stream bends toward a comb, you are watching a small visible clue to a much larger truth. Water is not a passive liquid. It is electrically textured. It carries hidden orientation, hidden attraction, hidden responsiveness. And static electricity itself, though familiar from crackling sweaters and tiny shocks from doorknobs, is not a toy phenomenon. It matters in dust behavior, lightning buildup, printing technology, air filtration, industrial safety, and the way tiny particles cling to surfaces. A charged object can attract dust for the same basic reason it can bend water. Charges and polarizations create forces that ordinary sight cannot see. In a photocopier or laser printer, controlled static charges help place toner powder exactly where an image should form. In some filters, charge fibers help capture small particles from air. In storms, charge separation inside clouds can build until the air breaks down, and lightning suddenly bridges the imbalance. The curved water at your sink is a gentle version of a force family that can also split the sky. And perhaps that contrast is what makes it so powerful. The same invisible principle that tugs a thin stream of water sideways can, under larger and more violent conditions, become a lightning strike. The world does not need to change its rules to become dramatic. It only changes the scale. There is something deeply calming in seeing this through a simple experiment. A comb, a sink, a little friction, a narrow stream, and suddenly the hidden electrical nature of matter becomes visible. You do not need a giant machine to witness it. You only need the right arrangement of ordinary things. And once you see the water curve, the air around objects feels less empty. Surfaces feel less silent. Your own body feels less separate from the electrical world, because every touch, every rub, every small spark is part of the same deeper language of charge and attraction. So the next time a balloon clings to a wall, your hair rises after brushing, or a tiny shock jumps from your finger to metal, remember the bending stream. Remember that neutrality does not mean nothing is happening. Remember that matter is filled with small separations, small imbalances, small hidden alignments waiting for the right field to reveal them. A falling thread of water can become a quiet teacher, bending not because it has been touched, but because it has been understood by a force your eyes cannot see. And in that gentle curve, the ordinary world becomes a little less ordinary, showing you that even still air can carry influence, even a simple comb can shape motion, and even water can answer an invisible pull. Soap can break. Surface tension. Instantly. Touch the surface of calm water with a trace of soap, and the water can seem to flinch. A moment before, it looked still, smooth, and quietly held together, like a thin, invisible skin had been stretched across it. Then one small drop of soap arrives, and suddenly pepper grains race away, floating objects shift, colors break apart, and the surface that seemed peaceful begins to reorganize itself almost instantly. This happens because water is not only a liquid filling a container. At its surface, it behaves like a stretched film under tension. Water molecules inside the liquid are pulled in many directions by neighboring molecules, so their attractions mostly balance. But molecules at the surface have no water molecules above them pulling upward in the same way, so they are pulled more strongly inward and sideways. This creates surface tension, a kind of invisible tightness that makes the surface resist being stretched. It is why small insects like water striders can stand on ponds without sinking, why tiny droplets bead up into rounded shapes, why a carefully placed needle or paperclip can sometimes float even though the material itself is denser than water, and why water can hold together in ways that look stronger than a liquid should. But soap changes this balance. Soap molecules have a special structure. One end is attracted to water, while the other end avoids water and prefers oils, grease, or air. When soap reaches the surface, its molecules slip between water molecules and weaken the attractions holding the surface tightly together. The surface tension drops, and it can drop very quickly. That sudden change creates motion because the surface is no longer pulling evenly everywhere. Imagine a stretched fabric being pulled equally from all sides, and then one side suddenly loosens. The fabric would shift toward the stronger pull. Water does something similar. Where soap lowers the surface tension, the surrounding areas of cleaner water still have stronger tension, so they pull the surface away from the soapy region. This difference in surface tension drives a flow called the Marangoni effect, and it is the hidden reason behind many simple demonstrations that look almost magical. Sprinkle pepper on water, then touch the surface with a soapy finger, and the pepper shoots outward. The pepper is not afraid of soap. It is simply riding on the water surface as that surface rapidly moves away from the area where tension has been weakened. The soap has not pushed the pepper directly like a hand. It has changed the rules of the surface underneath it. A tiny soap-powered boat can move for the same reason. If a small paper or plastic shape floats on water and soap is placed at the back, the lowered surface tension behind it allows the stronger tension in front to pull the boat forward. For a few moments, the boat seems self-propelled, but its fuel is really in balance. Once the soap spreads out and the tension becomes more even again, the motion fades. This is the key lesson. Soap does not break surface tension in the sense of destroying water's surface completely. It reduces it, disrupts it, and creates uneven forces that can produce sudden movement. That difference matters, because real science is often more interesting when it is precise. Soap is powerful, not because it makes water stop being water, but because it changes how water molecules hold hands at the boundary. And this same property is why soap is so good at cleaning. Water alone has relatively high surface tension, so it does not always spread easily into tiny cracks, fibers, oily films, or greasy surfaces. Soap lowers the surface tension, helping water-wet surfaces more effectively. At the same time, soap molecules surround oils and grease with their water-loving ends facing outward, allowing oily dirt to be lifted and carried away. This is why washing is not just rinsing harder. It is chemistry and physics working together. Reduced surface tension helps water spread, and soap's structure helps loosen substances that water alone struggles to remove. This is also why soap bubbles can form. Pure water has surface tension, but its surface is too fragile and short-lived to stretch into large stable films. Soap lowers the tension and creates a more flexible film that can survive long enough to become a bubble. But in this topic, the most important thing is not the bubble itself. It is the instant transformation at the surface. Soap reveals that the top layer of water is an active place, a thin border where molecular attractions shape visible behavior. You usually do not notice this border because it is transparent, silent, and always there. But place a drop of detergent on water holding pepper, or touch a greasy plate with soapy water, or watch a drop spread across a surface that plain water avoided, and you are seeing the hidden tension of liquids being rewritten. There is something quietly profound in that. A surface can look calm while holding invisible strain. A small disturbance can travel across it faster than expected. A tiny change in molecular attraction can rearrange an entire visible pattern. The world often changes this way, not by a giant force striking from outside, but by a small shift at the boundary where things meet. Soap works at boundaries between water and air, water and oil, water and skin, water and fabric, water and dirt. It teaches that edges matter, interfaces matter. The place where two substances meet is not passive. It can decide whether water beads or spreads, whether grease clings or lifts away, whether pepper rests or scatters, whether a tiny boat sits still or glides forward. And once you understand this, even washing your hands becomes less ordinary. The soap is not merely making foam. It is lowering surface tension, helping water reach more places, surrounding oils and particles, and allowing them to be rinsed away. A daily act becomes a small act of molecular engineering. So the next time you see pepper burst away from a soapy finger, do not see it as a simple trick. See it as the surface of water revealing its hidden strength, then losing that strength in one small region, creating motion from imbalance. See the invisible skin tighten, loosen, and pull itself into a new arrangement. See how a single drop can change not the whole ocean, but the rules at the edge. And let that stay with you. Sometimes the most dramatic changes begin at the surface, where forces too small to see decide what the visible world will do next. Smoke rings hold their shape through vortices. A smoke ring looks like a ghost learning how to keep its shape. It slips out into the air as a soft grey circle, delicate enough to vanish with a breath, yet organized enough to travel forward for a surprising distance without falling apart immediately. At first it seems almost impossible because smoke usually spreads, thins, and dissolves into the room. You expect it to become a cloud, not a moving ring. But a smoke ring survives for a while because it is not just smoke shaped like a circle. It is a vortex ring, a rotating structure in the air where the smoke is carried along by a rolling motion that continuously folds the air around itself. Imagine a wheel rolling forward, but instead of rubber and metal, the wheel is made of air turning through itself. The smoke simply makes that motion visible. The real structure is the moving vortex, and the smoke is like ink tracing its outline. When a puff of air is pushed through a round opening, such as from a smoke ring toy, a dolphin's blowhole, a volcano vent, or even someone carefully shaping smoke with their mouth, the air at the center moves forward faster than the air near the edge. The edge drags against the still air outside, slowing slightly and curling backward. That difference creates rotation. The air rolls into a donut-like shape, with the inside of the ring circulating around the core while the whole ring travels forward. This is why a good smoke ring does not behave like a simple cloud. A cloud is mostly drifting and spreading. A vortex ring is organized motion. It carries itself along because the rotating flow helps preserve its boundary for a time, pulling surrounding air into a stable pattern and keeping the smoke gathered along the rolling structure. But the stability is temporary. The ring is not a solid object. It has no skin, no wall, no permanent edge. It lasts only as long as the surrounding air stays calm enough and the vortex has enough energy to maintain its form. Air resistance, turbulence, temperature differences, nearby movement, and tiny instabilities slowly weaken it. The ring stretches, wobbles, breaks, and finally dissolves into ordinary smoke. What looked like a self-contained object was actually a pattern borrowing matter for a moment. That is one of the most important lessons of vortices. Sometimes the thing you see is not a thing at all, but motion holding a shape. A whirlpool in water, a tornado in air, the swirling wake behind a moving object, even the small spiral that forms when milk enters coffee. These are not objects in the way a stone is an object. They are organized flows. They exist because motion has arranged itself into a structure that can persist. A smoke ring is especially beautiful because it lets your eyes see this truth clearly. The smoke is not the cause of the ring's strength. It is the visible passenger riding on a hidden current. In clean air, the same vortex could exist almost invisibly, but with smoke, vapor, or dust inside it, the invisible architecture appears. This is why dolphins can create underwater bubble rings that look strangely similar. In water, the vortex ring carries bubbles instead of smoke. And because water is denser than air, the motion can look even more sculptural. Volcanoes can sometimes produce giant vortex rings when gas is released through a circular vent in the right pulse. Engines and cannons can generate vortex rings too, and scientists study them because they reveal how fluids move, mix, transport energy, and form coherent structures. Even your own body depends on fluid motion in ways that are far more complex than a simple ring. Blood flow, breathing, and the movement of air through the lungs all involve patterns that can become smooth, swirling or turbulent depending on speed and shape. But the smoke ring gives you the simplest visible doorway into this world. It shows that air is not empty stillness. Air can roll, it can curl, it can carry form. It can behave almost like an invisible material, shaping itself into patterns that last just long enough to be noticed. And there is something quietly philosophical in that. A smoke ring has no fixed substance, because the air and smoke inside it can change as it moves. Yet the pattern continues for a while, like a melody that remains recognizable even though each note fades as the next one arrives. Its identity is not in the particles alone, but in the relationship between motion and shape. That idea appears throughout nature. Waves in the ocean are not made of one permanent piece of water traveling across the sea. They are patterns of motion passing through water. A flame is not one stable object. It is a continuous process of hot gases, reactions, and flow. A smoke ring belongs to this family of temporary forms, things that exist not by holding still, but by moving correctly. And maybe that is why it feels so mesmerizing. It reminds you that stability does not always mean stillness. Sometimes stability is motion arranged in the right way. The ring survives because it turns. It holds its shape because it is constantly circulating. Stop that motion and the shape disappears. So when you watch a smoke ring drift through a room, do not see only smoke. See a spinning tunnel of air made visible for a few seconds. See a soft machine built from flow. See the air folding around itself, carrying a pattern forward without a solid surface to protect it. And when it finally breaks apart, let that ending teach you something too. Many forms in nature are not meant to last forever. They appear when energy, shape, and motion briefly agree, and they vanish when that agreement fades. A smoke ring is fragile, yes, but while it lives, it is not random. It is physics drawing a circle in the air, a silent reminder that even emptiness can organize itself, and that sometimes the most delicate shapes are held together not by matter, but by movement. Ferrofluids reveal magnetic field shapes. A ferrofluid looks like a liquid that has discovered how to grow thorns. Bring a magnet near it, and the smooth, dark surface suddenly rises into sharp peaks. Black needles, rippling crowns, and strange alien landscapes that seem too organized to belong to a fluid. It is easy to look at it and imagine some kind of living metal, but the real explanation is more interesting because it shows how a hidden magnetic field can become visible through matter. Ferrofluid is not ordinary liquid metal. It is usually a liquid, such as oil or water, filled with extremely tiny magnetic particles, often particles made from iron oxide. These particles are so small that they can remain suspended instead of simply sinking to the bottom, and they are coated with special molecules that help keep them from clumping permanently together. Without that coating, The particles would rush toward one another, form lumps, and the fluid would lose the smooth, responsive behavior that makes it so strange. But when they are properly suspended, the liquid remains fluid while also responding strongly to magnetic fields. In simple terms, the liquid becomes a crowd of tiny magnetic grains carried inside a flowing body. When no magnet is nearby, the surface may rest quietly, dark and glossy. But when a magnetic field appears, the particles inside the liquid begin to align with it. The stronger the field, and the sharper its changes from place to place, the more strongly the fluid is pulled and shaped. This is why ferrofluid does not merely slide toward a magnet like a simple object being attracted. It forms patterns. The magnetic force tries to pull the fluid into regions where the field is stronger, while gravity and surface tension try to keep the surface smoother and lower. Surface tension wants to reduce the surface area, smoothing out bumps. Magnetism wants to raise peaks where the field pulls upward. Gravity wants to pull everything down. The spikes appear when these forces reach a kind of tense compromise. The surface becomes unstable in a beautiful way, breaking from smoothness into pointed shapes. This is known as the Rosenzweig instability, though you do not need the name to feel the wonder of it. What matters is the idea. The spikes are not decoration added from outside. They are the fluid's answer to an invisible field. They show where magnetic influence is strong enough to reshape the surface against the forces that normally keep liquids smooth. But it is important to be honest about what you are seeing. Ferrofluid does not reveal magnetic field lines exactly like a perfect drawing in a textbook. It reveals the effect of the field on a responsive material. The pattern depends on the magnet's strength, the distance from the magnet, the shape of the container, the thickness of the fluid, the amount and size of the particles, the carrier liquid, gravity, and surface tension. So the spikes are not a pure map of magnetism alone. They are a conversation between magnetism and the fluid's own physical properties. This makes the phenomenon even richer because it reminds you that invisible forces do not appear in isolation. They become visible only through what they act upon. A magnetic field by itself cannot be seen with your eyes. It has no color, no smoke, no glowing outline, but place ferrofluid inside it. And suddenly, the field seems to carve the liquid into sculpture. The unseen becomes readable through response. This is why ferrofluid feels so powerful as a demonstration. It turns an abstract idea into something you can watch. You are not just being told that fields exist around magnets. You are seeing matter rearrange itself because of them, and that idea reaches far beyond a small dish of black liquid. Ferrofluids have real uses because their movement can be controlled without touching them directly. They can form seals in rotating shafts, especially in places where a liquid seal can be held in place by magnets. They can help in loudspeakers by carrying heat away from voice coils and damping motion. They can appear in sensors, dampers, and research systems, where a fluid that responds to magnetic fields is useful. Scientists have also explored magnetic nanoparticles in medicine, including ideas such as targeted drug delivery or magnetic heating for treatment research. Though real medical use depends on strict design, safety, and control, the same basic wonder remains. If matter can be made responsive enough, a field can guide it, hold it, move it, or shape it without a visible hand. There is something deeply calming and unsettling in that. The ferrofluid sits there as a liquid, but it carries a hidden sensitivity. It waits for a field, and when the field arrives, its surface becomes a landscape of forces. This makes you look differently at every magnet you have ever held. A magnet may seem like a simple solid object, but around it is a structured region of influence, spreading through space, curving, strengthening, weakening, and interacting with materials in different ways. Most of the time you cannot see that structure. You only notice it when iron filings line up, when a compass needle turns, or when ferrofluid lifts itself into spikes. The field was there before the demonstration. The demonstration only gives it a language, and perhaps that is the quiet lesson hiding in the black peaks. Reality is filled with shapes that do not appear until the right material is present to reveal them. A force can be real long before it becomes visible. A pattern can exist long before you have the tool to see it. The ferrofluid does not create the magnetic field. it translates it. It turns silent influence into form. So when you watch those dark spikes rise toward a magnet, do not see only a strange liquid trick. See a hidden architecture pressing into matter. See surface tension and gravity trying to smooth the world while magnetism pulls it into points. See thousands of tiny particles, suspended and restless, aligning together until the whole liquid seems to answer as one. And let that image stay with you. Some parts of the world are not invisible because they are absent. They are invisible because nothing nearby is sensitive enough to show them. Ferrofluid becomes sensitive. It listens to the magnet, and in listening, it gives the unseen a shape. Superconductors can levitate magnets. A magnet floating above a frozen ceramic disc can make the table beneath it feel less like furniture and more like a doorway into another version of matter. At first, the scene looks impossible. A small magnet sits in the air without strings, without a fan, without visible support, sometimes even locked so firmly that it can hang below the material or glide along a magnetic track, like it has been caught inside an invisible groove. But this is not anti-gravity, not magic, and not a trick of hidden machinery. It is superconductivity, one of the most extraordinary states matter can enter when certain materials are cooled below a critical temperature. In ordinary metals, electrical current always faces some resistance. Electrons move through the material, but they constantly lose energy through interactions with the structure around them, and that lost energy often becomes heat. This is why wires warm up when too much current flows through them. But in a superconductor, something radically different happens. Below the right temperature, electrical resistance drops to zero, meaning current can flow through the material without the usual energy loss. That alone is already astonishing, because it means a current in a superconducting loop can keep circulating for an extremely long time without needing a battery to constantly push it along. But superconductors do something even stranger. They respond to magnetic fields in a way ordinary materials do not. When a material becomes superconducting, it can push magnetic fields out of its interior. This is called the Meissner effect, and it is one of the key reasons a magnet can levitate above a superconductor. The superconductor does not simply repel magnets in the same way two ordinary magnets repel each other. It creates surface currents that generate an opposing magnetic field, reshaping the magnetic environment so that the field is kept from entering the superconducting region. The result can be a stable repulsion strong enough to lift a magnet against gravity. The magnet floats because gravity is pulling it down while magnetic forces are pushing it away. And when those forces balance, the magnet rests in mid-air. But the most haunting version of this effect appears with many high-temperature superconductors, especially Type II superconductors cooled with liquid nitrogen. These materials do not always expel magnetic fields perfectly. Instead, small bundles of magnetic field can pass through tiny regions inside the superconductor. These bundles are often called flux lines or vortices, but you can think of them more simply as thin threads of magnetic field trapped through the material. If the material has tiny imperfections, those magnetic threads can become pinned in place. This is called flux pinning, and it is what makes the levitation look so strangely stable. The magnet is not only pushed away, it is held in a kind of magnetic memory. It can be locked at a certain height, resisted when you try to move it sideways, and even remain suspended beneath the superconductor if the magnetic field has been pinned in the right configuration. This is why some demonstrations show a superconductor floating above a magnetic track and staying aligned as it moves. It is not merely hovering like a balloon, it is trapped in a magnetic relationship, held by the pattern of field lines that the superconductor refuses to let change easily. To understand how strange that is, imagine placing an object in space and having it remember its position not because of a hook or shelf, but because the magnetic field around it has become frozen into a stable arrangement. The superconductor acts almost like a material that says, "This is the field pattern I accepted when I became cold enough, and now I will resist changes to it." That resistance to change is what gives the floating magnet its eerie steadiness. But there are limits, and those limits matter. A superconductor only behaves this way below its critical temperature. Warm it up too much and the effect disappears. It also has limits for how much magnetic field and how much electrical current it can handle before superconductivity breaks down. Not every superconductor floats magnets dramatically, and not every magnet-superconductor combination produces a clean demonstration. The material, temperature, magnetic strength, geometry, and cooling conditions all matter. Many classic demonstrations use ceramic superconductors cooled by liquid nitrogen because liquid nitrogen is cold enough for some so-called high-temperature superconductors and is easier to handle in laboratories than liquid helium, though it is still extremely cold and must be treated carefully. The word high temperature can be misleading here. It does not mean warm in the everyday sense. It only means high compared with older superconductors that needed even colder conditions. This is part of why superconductivity is both powerful and difficult. If we had materials that superconducted easily at room temperature and normal pressure, the world could change dramatically. Power grids could lose far less energy as electricity travels. Magnets for medical imaging, particle accelerators, and transportation systems could become more efficient. Magnetic levitation trains could become more practical in more places. Electronics and sensors could be redesigned around currents that do not waste energy in the usual way. But real superconductors are demanding. They often need extreme cooling, careful engineering, and protection from conditions that would destroy the superconducting state. So the floating magnet is not just a beautiful trick. It is a glimpse of a future that is still partly out of reach. It shows what matter can do, while also reminding us how hard it is to make matter do it conveniently. What makes this phenomenon so deeply fascinating is that superconductivity is not just a stronger version of ordinary conductivity. It is a collective state. The electrons inside the material are not behaving like separate, scattered individuals in the usual way. Under the right conditions, they enter a coordinated quantum state, where their behavior becomes linked across the material. You do not need heavy equations to feel the meaning of that. In ordinary matter, countless tiny interactions create friction, loss, and resistance. In a superconductor, at low enough temperature, a kind of deep coordination emerges, and that coordination changes what the material is capable of. It can carry current without resistance. It can exclude magnetic fields. It can pin magnetic structures so strongly that a magnet seems suspended in empty air. The object on the table becomes a quiet lesson in how the microscopic world can produce macroscopic wonder. You are not seeing atoms directly. You are seeing the consequence of their collective behavior, large enough to lift a visible object. And maybe that is why superconducting levitation feels so different from ordinary magnet tricks. With two magnets, repulsion can feel familiar. You push one near another and feel a force. But with a superconductor, there is a sense of something more disciplined, more uncanny. The magnet does not just bounce away. It can stabilize. It can lock. It can move along a track while maintaining its height. It can appear to defy the casual categories of falling and resting. The table says the object should sit. Gravity says it should drop. But the superconducting state says there is another arrangement possible, one where electrical currents and magnetic fields create a silent architecture strong enough to hold matter in place. And there is a soft philosophical lesson here if you let the science speak slowly. Matter is not fixed in one ordinary personality. Cool it enough, arrange it correctly, and it can reveal a hidden mode of existence. A ceramic disc that looks dull and lifeless at room temperature can, when lowered into deep cold, become a stage for levitation. The transformation is not visual at first. The material may look almost the same. But inside, its rules have changed. This is often how the deepest changes in nature appear. Not as a new shape you can immediately see, but as a new behavior under the surface. So when you watch a magnet hover above a superconductor, do not imagine gravity being broken. Imagine a deeper agreement being formed. Cold matter entering a quantum state, electrical resistance vanishing, magnetic fields being expelled or pinned, and a small magnet finding a stable place in that invisible arrangement. It is a reminder that the world still contains states of matter that feel like secrets. Some of them are not hidden in distant galaxies or inside impossible machines, but in materials placed into the right conditions. A magnet floats, and for a moment, The ordinary heaviness of the world seems negotiable. Not because the laws of physics have failed, but because they have revealed a stranger chapter than the one we usually live inside. Plasma is not gas, liquid, or solid. A neon sign glowing in the dark is not simply filled with colored gas. It is showing you matter after it has been electrically awakened. You grow up learning 3 familiar states of matter. Solids keep their shape. Liquids flow and take the shape of a container. Gases spread outward and fill the space around them. These categories feel complete because they explain tables, oceans, clouds, breath, rain, ice, steam, and almost everything you touch in daily life. But beyond those familiar forms is another state so common in the universe that calling it exotic almost feels backwards. Plasma is often called the 4th state of matter, and it is not a solid, not a liquid, and not an ordinary gas. It can look like a glowing mist, a lightning branch, a solar flare, a ribbon of aurora, or the soft light inside a neon tube. But what makes plasma different is not only that it shines. Its deeper identity comes from electrical separation. In an ordinary gas, atoms and molecules are mostly neutral. They may fly around quickly, collide, spread, and mix, but each atom still holds its negatively charged electrons close enough that the whole particle behaves as a balanced unit. In a plasma, enough energy has been added that some electrons are stripped away from atoms, leaving behind positively charged ions and free electrons moving among them. This means the material is no longer just a collection of neutral particles. It becomes a charged environment, a restless sea of electrons and ions that can respond strongly to electric and magnetic fields. That single change transforms everything. A gas may drift with the wind, but a plasma can twist along magnetic fields, carry electrical currents, produce light, form filaments, and behave collectively, almost like a crowd reacting to invisible signals. The particles inside it do not simply collide like tiny billiard balls. They influence one another from a distance through electrical forces. Because positive and negative charges attract, repel, separate, and move, plasma can create waves, arcs, loops, sheets, and instabilities that have no simple equivalent in ordinary air. This is why lightning does not look like a smooth glowing cloud. It branches, it searches. It creates a hot, ionized channel through the air where electricity can suddenly flow. For a brief moment, the air itself becomes plasma, heated to extreme temperatures, glowing because atoms and molecules are excited and ionized, then collapsing back as the channel cools. The aurora works differently, but carries the same secret. Charged particles from the sun travel along Earth's magnetic field and collide with atoms high in the atmosphere, causing them to glow in curtains of green, red, and violet light. The sky becomes a screen where charged particles and magnetic fields write slow, luminous motion. And the sun itself is not a ball of fire in the ordinary sense. It is a vast sphere of plasma, so hot that atoms are stripped into nuclei and electrons, with nuclear fusion occurring in its core and magnetic fields shaping activity at its surface. Solar flares, prominences, and coronal loops are not flames licking upward like candlelight. They are plasma guided by magnetic structures on a scale larger than Earth. In fact, most of the visible matter in the universe is thought to be plasma, because stars are plasma, and stars dominate what we see across cosmic distances. So the strange state you meet in a neon sign is also the state that makes the stars shine. The same broad category connects a laboratory tube to the heart of the sun, a lightning strike to the glow of distant galaxies. But plasma is not always extremely hot in the everyday sense. This is where the topic becomes more subtle. Some plasmas are thermal, meaning the ions and electrons are all very hot and energetic. Others are called non-thermal or cold plasmas, where the electrons may be highly energetic, while the heavier particles remain much cooler. That is why certain plasma devices can interact with surfaces without simply burning everything they touch. Cold plasmas are studied and used for sterilization, surface treatment, materials processing, and medical research because reactive particles and ultraviolet light can affect microbes or surfaces in useful ways. Fluorescent lamps and neon signs use low-pressure gas and electricity to create glowing plasma inside glass. The color depends on the gas and the coatings involved. Neon gives a reddish-orange glow, while other gases or phosphor coatings can produce different colors. A plasma globe, the kind with glowing tendrils that follow your fingers, shows electric fields shaping ionized gas into moving filaments. But it is important not to oversimplify. Plasma is not just electricity, and it is not simply fire. Many flames contain small numbers of ions and electrons, but an ordinary candle flame is only weakly ionized and does not behave like the plasmas found in stars, lightning, or specialized devices. Fire is a chemical reaction producing hot gases and light. Plasma is defined by ionization and collective electrical behavior. Sometimes they overlap, but they are not the same thing. This distinction matters because plasma teaches a deeper lesson about states of matter. A state is not only about how something looks, but about how its particles are arranged, how they move, and how they respond to forces. Ice feels solid because its molecules are locked into a structure. Water flows because its molecules can slide past one another. Steam expands because its molecules move freely. Plasma goes further. Its particles are not only moving freely, they are electrically divided. And that division makes the whole material sensitive to fields in a powerful way. This is why scientists care about plasma so much. To build fusion reactors, we must learn how to confine plasma hot enough for atomic nuclei to fuse, without letting it touch and destroy the walls of the container. Since no ordinary material can hold something that hot directly, researchers use magnetic fields to guide and trap it, especially in devices such as tokamaks and stellarators. Fusion research is one of humanity's most ambitious attempts to work with plasma, because it asks whether we can control on Earth the kind of process that powers stars. Plasma is also used in semiconductor manufacturing, where it can etch tiny patterns into materials with great precision. It appears in electric propulsion for spacecraft, where ionized particles can be accelerated to produce gentle but efficient thrust over long periods. It appears in welding arcs, plasma cutting tools, and high-energy physics experiments. So plasma is not just a glowing curiosity, it is both a natural cosmic state and a technological tool. But perhaps the most beautiful part is how plasma changes your sense of emptiness. The space around Earth is not completely empty. The solar wind is a plasma flowing outward from the sun, interacting with planets, magnetic fields, and atmospheres. Around Earth, invisible magnetic structures guide charged particles in vast regions that can become active during solar storms. What looks like empty space is, in many places, a thin plasma environment filled with motion, charge, and field. The universe is not only made of quiet rocks and neutral gases, it is filled with electrically responsive matter moving through invisible magnetic landscapes. Once you understand plasma, the glowing edge of a lightning bolt, the shimmer of an aurora, and the steady light of a star stop feeling like separate wonders, they become chapters in the same story. Matter given enough energy to split into charged pieces, then shaped by forces that ordinary matter barely reveals. And maybe that is why plasma feels so alive, even when it is not alive. It flickers, branches, pulses, follows fields, forms curtains, arcs, jets, and loops. It behaves less like a passive substance and more like motion with a nervous system, though the nerves are electric and magnetic, not biological. It reminds you that matter has hidden thresholds. Add enough energy, change the conditions, and the familiar categories open into something stranger. The air that seems harmless can become a lightning channel. A glass tube of gas can become a glowing sign. The sun can be understood not as fire above us, but as plasma held together by gravity, shining because of processes deep inside it. So when you see a neon sign humming in a window, or lightning flashing through a storm, or auroras waving over polar skies, do not see only light. See matter crossing a boundary. See atoms partly taken apart and reorganized into a charged sea. See a state that is rare on your table, but common among the stars. And let it gently unsettle the old lesson you learned as a child, because solid, liquid, and gas were never the whole story. They were only the beginning of matter's vocabulary. And plasma is one of its brightest, strangest words. Aerogel can be almost weightless. Hold a piece of aerogel in your hand, and your brain may struggle to believe it is holding anything at all. It can look like frozen smoke, like a fragment of cloud that somehow became solid, like a pale blue ghost of glass with almost no body inside it. And that is not far from the truth, because aerogel is one of the lightest solid materials ever made. Not because it is imaginary or hollow in the simple sense, but because most of its volume is empty space. A typical silica aerogel begins with a gel, a wet network of solid material filled with liquid. In an ordinary drying process, that delicate network would collapse as the liquid evaporates, because surface forces would pull the tiny structure inward. But aerogel is made through special drying methods that remove the liquid while preserving the fragile internal framework. What remains is a solid skeleton full of nanoscale pores, so open and airy that the material can be more than 90% air. In some aerogels, the solid part is only a tiny fraction of the whole object. That is why a piece can appear substantial in shape, yet feel unbelievably light, almost like matter has been reduced to a whisper. But aerogel is not weightless. It still has mass. It still obeys gravity. The word almost weightless captures the feeling better than the literal truth. Compared with ordinary solids, it can have an extremely low density, meaning a large-looking piece may contain very little actual solid material. This is the first lesson aerogel teaches. Heaviness is not simply about size. A large object can be light if its internal structure is mostly empty, while a small object can be heavy if its atoms are packed densely. Aerogel invites you to stop judging matter by its outer shape and start asking what is hidden inside. And what is hidden inside aerogel is a maze, a microscopic network of thin solid strands and tiny pores that trap air in place. This trapped air is one of the reasons aerogel is such an extraordinary insulator. Heat usually moves through materials in several ways. It can travel through solid contact, move with flowing air, or radiate as infrared energy. Aerogel makes all of these difficult. Its solid framework is so sparse that heat has very few solid pathways to travel through. Its pores are so tiny that air inside them cannot circulate easily, so heat cannot be carried away by moving air in the usual way. Some aerogels are also designed to reduce heat radiation. The result is a material that can protect against extreme temperature differences while weighing very little. This is why aerogels have been used in spacecraft and scientific instruments, where every gram matters, and insulation can be critical. NASA has used aerogel to insulate equipment and to capture high-speed dust particles from comets and space without completely destroying them, because the material can gradually slow tiny particles inside its porous body. Imagine a piece of material so light it looks barely real, yet so carefully structured that it can help protect machines in space or catch ancient dust crossing the solar system. That contrast is what makes aerogel so fascinating. It looks weak, and in some ways it is fragile. Many silica aerogels can crumble, crack, or shed dust if handled roughly. They are not like steel or hard plastic. Their strength depends on the type, formulation, and structure. And some newer aerogels or aerogel composites are much tougher than the delicate classic pieces people often see in demonstrations. But the fragility is part of the story. Aerogel is not impressive because it behaves like every other solid. It is impressive because it is a solid pushed close to the edge of emptiness while still holding a form. Its internal structure is so fine that light passing through it scatters in a special way, often giving silica aerogel that faint bluish glow, similar in principle to why the sky appears blue. Longer wavelengths may pass through more easily, while shorter blue wavelengths scatter more, creating a soft, otherworldly color inside a material that is mostly air. This makes aerogel feel less like an object and more like a captured atmosphere. But beneath the beauty is practical engineering. Aerogels can be made from silica, carbon, metal oxides, polymers, and other materials, and each kind has different properties. Carbon aerogels can conduct electricity and may be useful in energy storage or filtration. Polymer aerogels can be more flexible and mechanically resilient. Silica aerogels are famous for their low density and insulation. Some aerogel blankets are made by combining aerogel particles with fibers, creating flexible insulation used in buildings, industrial pipes, cold environments, and high-temperature systems. This matters because the future of materials is not only about making things stronger or harder. Sometimes it is about controlling structure at tiny scales so that matter behaves in a new way. Aerogel is a perfect example of architecture becoming a property. The material is not only defined by what it is made of, but by how it is arranged. The same basic chemical substance, if packed differently, could become ordinary glass, powder, or a fragile translucent solid lighter than anything your instincts expect. Structure changes destiny. That idea reaches far beyond aerogel. Bones are strong partly because of internal structure. Wood is useful because of its fibrous architecture. Foam, coral, sponge, and honeycomb forms all show that emptiness inside a material is not always weakness. It can reduce weight, redirect forces, trap air, absorb energy, and create surprising performance. Aerogel takes that principle to an extreme. It is not empty in the way a box is empty with one large hollow center. It is empty in a far stranger way, filled with countless tiny voids distributed through a delicate solid web. That is why it can be both present and barely there. And perhaps this is the quiet emotional pull of aerogel. It challenges the way you think about substance. You tend to trust what feels heavy. You tend to associate weight with importance, density with reality, solidity with strength. But aerogel says that something can be mostly absence and still matter. Something can be light and still protect. Something can look like a ghost and still perform work no ordinary material could do as efficiently. There is no need to exaggerate it into fantasy. It does not float away like smoke. It does not violate gravity. It does not make objects weightless. But the truth is already strange enough. Humans learned how to preserve a microscopic skeleton after removing almost everything that filled it, creating a solid that feels like a contradiction. So the next time you see aerogel resting on someone's palm, pale and cloudy and almost unreal, do not see only a scientific novelty. See a lesson in hidden architecture. See a material made not by adding more, but by carefully taking away without letting the structure collapse. See insulation born from trapped stillness, lightness born from emptiness, and strength reimagined not as mass, but as design. Aerogel reminds you that the world is not always built by filling space. Sometimes the most extraordinary material is made by preserving the spaces between, by giving emptiness a framework, and by proving that even near nothing can become something powerful when arranged with enough care. Graphene is one atom, thick but extremely strong. A sheet of graphene is so thin that calling it a sheet almost feels too generous, because it is only one atom thick, yet it can be stronger than materials that look far more solid and permanent. Imagine taking carbon, the same element found in pencil graphite, charcoal, diamonds, and living cells, and arranging its atoms into a flat honeycomb pattern so delicate that millions of layers stacked together would still be extremely thin, but so tightly bonded that the sheet becomes astonishingly strong for its size. That is graphene, a single layer of carbon atoms linked in a two-dimensional lattice, almost like a microscopic chicken wire pattern made from one of nature's most versatile elements. What makes it strange is not only its thinness, but the combination of properties that appear when carbon is arranged this way. In graphite, the material inside a pencil, carbon atoms are also arranged in sheets, but many layers sit on top of one another and can slide apart easily. That sliding is why graphite leaves a mark on paper, but isolate just one layer and the story changes. You get a material that is incredibly strong in tension, excellent at conducting electricity, excellent at conducting heat, nearly transparent, flexible, and extraordinarily light. It is not indestructible, and it is not a magical material that automatically solves every engineering problem, but it is one of the most remarkable materials ever studied because it shows how much power can hide inside arrangement. The carbon atoms in graphene are joined by very strong bonds, and because every atom belongs to the surface, there is almost no wasted interior. In a normal thick material, many atoms sit buried inside, adding weight and volume. In graphene, every atom is part of the active structure. It is all surface, all framework, all participation. That is why people often describe it as one of the strongest known materials when measured by tensile strength, meaning how much pulling force it can withstand before breaking. A perfect sheet of graphene can be extraordinarily strong, but real-world graphene often contains defects, grain boundaries, wrinkles, contamination or damage, and those imperfections can weaken it. This is important because the most exciting version of graphene is often the ideal laboratory version. While the industrial challenge is making large, clean, consistent, affordable graphene and connecting it to other materials in useful ways. Science is not only about discovering a wonder, it is about learning how to make that wonder reliable outside a perfect experiment. Still, the truth remains astonishing. A material 1 atom thick can resist tearing with a strength that feels completely out of proportion to its visible presence. If you could hold a perfect sheet large enough to see, it would appear almost transparent, because one layer of atoms absorbs only a small amount of visible light. It would be hard to believe something so nearly invisible could have such strength. And that is the first deeper lesson of graphene. Strength does not always announce itself through thickness. Sometimes strength comes from bonds, geometry, and order. A wall can be thick and weak if its internal structure is poor. A material can be thin and powerful if its atoms are arranged with extraordinary efficiency. Graphene also conducts electricity in a very unusual and efficient way. Electrons can move through its flat carbon network with remarkable ease, which makes it interesting for electronics, sensors, and high-speed devices. But again, the story is careful, not exaggerated. Graphene is not automatically replacing silicon in every computer chip, partly because pure graphene does not naturally have a bandgap in the same way semiconductors like silicon do, and that makes it harder to turn electrical current fully on and off in the simple way digital electronics often require. So graphene is not a miracle shortcut that makes all existing technology obsolete. It is more like a new alphabet of material possibility. It may be used where its strengths match the problem. Transparent conductive coatings, sensitive detectors, composite materials, flexible electronics, membranes, heat spreaders, energy storage research, water filtration research, and advanced coatings. In composites, even a small amount of graphene or graphene-like material can sometimes improve strength, conductivity, or thermal performance depending on how well it is dispersed and bonded inside the host material. That depending matters. If the graphene clumps together, aligns poorly, or fails to connect with the surrounding material, its extraordinary properties may not fully appear. The hidden miracle must be integrated correctly, or it remains mostly potential. Graphene's thinness also makes it fascinating as a membrane. Because it is 1 atom thick, it can act as an extremely selective barrier if engineered carefully. Researchers explore graphene-based membranes for separating molecules, filtering water, detecting gases, or studying how substances pass through tiny pores. A sheet that is almost nothing can become a gatekeeper between worlds. It can be pierced with nanoscale openings, modified chemically, layered with other materials, or used as a platform where even a single molecule landing on its surface can change its electrical behavior. This is why graphene is so important for sensing. When your entire material is surface, every contact matters. There is no hidden bulk to ignore the outside world. The material is exposed, responsive, and sensitive. That gives it a strangely philosophical quality. Graphene is powerful, not because it hides behind thickness, but because it has no inside to retreat into. Everything that happens to it happens at the surface. Everything is contact. Everything is structure. And perhaps that is why it feels so different from older ideas of strength. We often imagine strength as heaviness, as armor, as more layers, more mass, more resistance through bulk. Graphene suggests another kind of strength, a strength of precision, a strength of being arranged so well that very little is needed. A strength that comes not from abundance, but from exactness. Its carbon atoms form a repeating pattern that is simple to describe yet difficult to master at scale. That pattern gives rise to properties that seem almost contradictory, flexible but strong, thin but conductive, nearly transparent but mechanically powerful. And because it is carbon, the same element that can become soft graphite or hard diamond depending on arrangement, graphene becomes a reminder that identity in matter is not only about ingredients. It is about architecture. Carbon as graphite writes softly. Carbon as diamond cuts. Carbon as graphene becomes a one-atom thick sheet with extraordinary strength and speed for electrons. The atoms are the same family, but the structure changes the story. This is one of the most important lessons materials science can teach. The future may not come only from discovering new elements, but from arranging known elements in new ways. The ordinary periodic table becomes extraordinary when geometry changes, and yet graphene's story also teaches patience. Many headlines have promised graphene revolutions, and some of those promises moved faster than the engineering could follow. Making tiny flakes is not the same as making huge flawless sheets. Measuring strength in a perfect sample is not the same as building bridges, aircraft, batteries, or screens from it. A material can be brilliant and still difficult to manufacture, connect, shape, protect, and scale. That does not make it less important, it makes it real. The most transformative materials often spend years moving from laboratory wonder to practical tool. Their first gift is not always a finished product. Sometimes it is a new way of thinking. Graphene teaches engineers to think in layers, surfaces, defects, bonds, and atomic precision. It teaches that a single layer can change electrical, thermal, and mechanical behavior. It teaches that the boundary between chemistry and engineering can become one atom thick. So when you hear that graphene is one atom thick but extremely strong, do not imagine a fantasy fabric that cannot break. Imagine something more truthful and more interesting. A carbon lattice so thin it almost disappears, yet so tightly bonded that it reveals the hidden power of structure. Imagine a material that turns surface into strength, lightness into advantage, and simplicity into possibility. Imagine holding, in thought, a sheet that is nearly invisible, but still capable of changing how we design sensors, coatings, composites, membranes, and devices. And let it gently unsettle your instincts, because the world keeps showing us that what seems small is not always weak. What seems thin is not always fragile. And what seems almost absent can still carry remarkable force when every part of it is arranged with purpose. Graphene is not a miracle because it breaks the laws of nature. It is a miracle because it follows them so beautifully that one layer of atoms becomes enough to make you question what strength really means. Sound can move small objects. A tiny bead floating in mid-air between two silent machines can make sound feel less like something you hear and more like something that has learned how to hold. You may think of sound as an experience inside your ears, a voice, a song, a vibration passing through the room and then fading into silence. But sound is also a physical movement through matter. It is made of compressions and rarefactions, tiny waves of pressure traveling through air, water, or another medium. And wherever there is pressure, there can be force. Most sounds around you are too weak to push objects in a dramatic way. A whisper will not move a grain of dust across a table. A song playing softly from a speaker will not lift a drop of water into the air. But when sound is focused, intense, and carefully arranged, especially at ultrasonic frequencies, too high for humans to hear, it can move, trap, spin, and even levitate small objects without touching them. This effect is not fantasy. It is called acoustic manipulation, and in its most striking form, acoustic levitation. The idea begins with a simple truth. Sound waves carry energy through a medium. As the wave passes, particles in the air or liquid move back and forth, creating tiny changes in pressure. If the wave is strong enough and shaped in the right way, those pressure changes can produce a steady force on small objects. In an acoustic levitation setup, scientists often use ultrasonic speakers or transducers aimed toward a reflector or toward another transducer. The sound waves meet and form stable regions in the air where the pressure pattern can hold a lightweight object in place. The object does not float because gravity has disappeared. It floats because the upward acoustic force balances the downward pull of gravity. The sound field becomes a kind of invisible shelf, made not from solid material, but from pressure. To your eyes, the bead or droplet may seem suspended in emptiness. To physics, it is sitting inside a carefully shaped landscape of forces. What makes this especially strange is that the sound can be completely inaudible to you. Ultrasonic sound is above the range of human hearing, so the room may feel quiet while a small object is being held in the air by vibrations too rapid for your ears to register. Silence, in that moment, becomes misleading. The air is not still. It is being organized at high speed, and the object in the middle is responding to a pressure structure your body cannot directly sense. This is why acoustic levitation often feels more mysterious than it really is. Nothing supernatural is happening. The object is simply small enough, light enough, and placed in a sound field strong enough for acoustic forces to matter. A heavy stone will not hover in the same setup. A large object would require far greater forces, and the energy involved would become impractical or dangerous. But tiny beads, foam pieces, droplets, grains, and small particles can be moved in remarkable ways. Researchers can shift the sound field to move objects from one position to another. They can make droplets rotate. They can bring small particles together or separate them. In liquids, sound can be used to guide cells, sort tiny particles, concentrate materials, or move droplets through microfluidic devices. This is sometimes called acoustic tweezing, because sound can act like a gentle tool for handling objects too small or delicate for ordinary mechanical contact. The advantage is beautiful. If you can move something with sound, you may not need to touch it with a solid instrument. That matters when the object is fragile, sterile, chemically sensitive, or microscopic. A cell, for example, can be influenced by a sound field without being grabbed by metal. A droplet can be suspended without resting on a surface that might contaminate it. A tiny sample can be mixed, positioned, or studied while floating freely. This makes sound not just a carrier of information, but a tool of control. It can become a hand made of pressure, yet the hand is subtle. It does not behave like fingers closing around an object. It works by shaping the environment around the object, guiding it towards stable positions where the forces balance. In air, the object is held by pressure differences and scattering effects. In liquid, the surrounding medium matters even more, because sound travels differently through water than through air, and the forces can be used to separate particles based on size, density, or compressibility. This is one of the most useful parts of acoustic manipulation. Different objects respond differently to the same sound field. That means sound can sort matter without needing labels or chemicals. Tiny particles in a flowing liquid can be pushed toward different paths. Cells can be concentrated into lines. Droplets can be controlled on small chips. In future technologies, sound may help build contactless laboratories where fluids, cells, and particles are handled with patterns of pressure instead of pumps, needles, or moving parts. But it is important to keep the science honest. Ordinary sound from a speaker in your room is not enough to safely levitate random household objects. Very loud sound can move air, shake surfaces, and even damage hearing. But acoustic levitation depends on controlled high-frequency fields, object size, and precise positioning. The object is not being lifted by sound in the vague sense of music or noise. It is being lifted by a carefully engineered pressure field. This distinction matters because the real phenomenon is more interesting than the exaggeration. It shows that the world is not moved only by obvious contact. A force can be distributed through a medium. A vibration can be arranged into a trap. A pressure wave can become a tool. And once you understand that, sound begins to feel larger than hearing. You start to realize that every sound has a physical side, even if it is usually too gentle to notice. When a bass speaker makes your chest vibrate, when a window trembles during thunder, when a glass hums near a loud note, you are feeling the mechanical nature of sound. Acoustic levitation is the refined, delicate, laboratory version of that same truth. It takes the raw idea that vibration can push and turns it into precision. It says, do not just make noise, shape the wave. Do not just fill space, organize pressure. Do not just hear sound, use it. There is something quietly profound in watching a droplet hover because of a force you cannot see and a frequency you cannot hear. The object seems free, but it is held by structure. The room seems silent, but it is full of motion. The air seems empty, but it has become a scaffold. And perhaps that is the lesson hidden inside acoustic levitation. Influence does not always need to be visible to be real. Some of the most delicate control in nature and technology comes from shaping the field around a thing rather than touching the thing itself. A small object can be moved not by being grabbed, but by being placed inside a pattern that gently tells it where to go. So the next time you hear a sound fade into a room, do not think of it only as something that enters the ear and disappears. Think of it as a traveling pressure, a moving arrangement, a physical event. Under ordinary conditions, it passes through you unnoticed, except as hearing. Under the right conditions, it can lift a bead, steer a droplet, sort a cell, or hold a tiny piece of matter in midair. Sound is not just vibration becoming experience. It is vibration becoming force. And in that quiet realization, the world grows stranger. Even something as invisible as a tone can reach into matter, not with a hand, but with pressure shaped so carefully that small things begin to move as if guided by silence itself. Light can be slowed dramatically in special materials. Light feels like the universe's fastest messenger, yet inside the right material, it can be slowed until it moves less like a cosmic arrow and more like a thought passing through a sleeping mind. In empty space, light travels at the ultimate speed limit of nature, so fast that it can circle Earth many times in a single second, and because of that, we often imagine light as something untouchable, unstoppable, almost impatient. It leaves the sun, crosses space, enters your eye, and gives you the world before you have time to wonder how it arrived. But light does not move the same way through every environment. When it enters glass, water, crystal, or certain specially prepared materials, it interacts with the atoms inside, and those interactions can delay the progress of the light wave. This is why a straw looks bent in a glass of water, why lenses can focus images, why prisms can split white light into colors, and why the world seen through thick glass can feel slightly displaced. The light is not simply getting tired, it is being influenced by the material it moves through. Its electric field disturbs the electrons in the atoms. The atoms respond, and the passing wave becomes a combined dance between light and matter. In ordinary glass, this delay is small, so light still seems almost instant to you. But in special laboratory conditions, scientists can slow light dramatically, not just by a little, but by astonishing amounts. In certain ultra-cold atomic gases, where atoms are chilled to temperatures close to absolute zero and prepared with carefully tuned lasers, a pulse of light can be slowed to the speed of a bicycle, a runner, or even slower. This sounds impossible until you realize that what is being slowed is not the basic speed limit of light in empty space, but the movement of a light pulse through matter. The pulse becomes deeply mixed with the atoms, almost like a message being passed through a crowd that briefly absorbs, delays, and releases it. One important method is called electromagnetically induced transparency, but you do not need the technical name to understand the wonder. Normally, a cloud of atoms might absorb a certain color of light and block it, but with another carefully chosen laser, scientists can make the atoms transparent to that light in a very narrow and controlled way. At the same time, this transparency comes with a strong delay, so the light pulse moves through the cloud much more slowly than it would through empty space. The material becomes transparent and delaying at once, like a doorway that opens but asks every traveler to move slowly. In even more surprising experiments, the information carried by a light pulse can be temporarily stored in the atoms and later released again. This is sometimes described as stopping light, but the honest version is more subtle and more beautiful. The light itself is not sitting there like a frozen beam in the air. The optical information is mapped into a collective state of the atoms, held briefly as a material memory, and then converted back into light. It is as if the light hands its message to matter, waits in another form, and then is born again as a pulse that continues its journey. That distinction matters because real science does not need exaggeration. The truth is already strange enough. Light, the thing we associate with speed, can have its motion reshaped so deeply by matter that it becomes slow, delayed, stored, and released. And this opens doors to technologies that depend not on making light brighter, but on controlling it more delicately. Slow light could help in optical communication, where information is carried by light through fibers and chips. It may help create buffers that temporarily hold optical signals, improve sensors, support quantum information experiments, and allow scientists to study the relationship between light and matter with extreme care. In quantum technologies, where information can be fragile and delicate, learning how to store and control light is especially important, because light is excellent at carrying information over distance, while atoms can be better at holding information in place. Slow light research tries to bridge those two strengths. Let light travel when movement is needed. Let matter hold the message when stillness is needed. But there are limits. You cannot slow light in a simple block of ordinary material to walking speed just by making the material thicker. You need very specific conditions, carefully prepared atoms or engineered structures, and the effect may work only for certain colors, pulse shapes, and environments. Some slow light systems are fragile, cold, complex, or difficult to use outside the lab. In other systems, such as photonic crystals or special waveguides, the structure of the material itself can guide and delay light by controlling how waves move through it. These are not magic tunnels. They are designed landscapes for light, built so that the wave has to move according to patterns created inside the material. The deeper lesson is that speed is not always a property of a thing alone. It can depend on the path, the medium, the interaction, and the hidden structure of the environment. A person running on a clear road moves differently than a person moving through a dense crowd. A message shouted across an empty field arrives differently than a message passed from person to person through a room. Light in empty space is the clear road. Light in special matter is the crowded room, the careful relay, the conversation with atoms. And once you understand this, light becomes more intimate. It is not just a beam crossing distance. It is a traveler whose journey changes depending on what it passes through. Matter is not simply in the way. Matter becomes part of the journey. This is why slow light feels so quietly unsettling. It challenges the simple picture of light as pure speed and matter as passive obstacle. Instead, it reveals a universe where even the fastest thing we know can be delayed by relationship. The atoms do not catch light with hands, but their internal structure shapes its passage. The pulse does not lose its identity completely, but it becomes partly entangled with the material response around it. The result is neither ordinary light nor ordinary matter, but a shared state moving at a pace that seems almost impossible compared with light's usual rush. So the next time you see sunlight pass through a window, or a lens bend an image, or a fiber optic cable carry signals across the world, remember that light is not always the untouchable sprint you imagine. Under the right conditions, it can be guided, slowed, delayed, and briefly written into matter like a secret kept by atoms. And perhaps that is the soft wonder hidden here. Even the fastest messenger in the universe can be taught patience, not by breaking the laws of physics, but by entering a place where motion becomes conversation, where brightness becomes memory, and where speed itself depends on the quiet structure of the world it moves through. Friction can create heat from motion. Rub your hands together in the cold, and you are performing one of the oldest energy transformations in the universe without thinking about it. At first, it feels like a small human habit, something simple and almost automatic. Your palms slide, the skin drags, and warmth appears where there was only motion a moment before. But that warmth is not coming from nowhere. It is motion-changing form. It is the energy of movement being scattered into the tiny, restless vibrations of matter. This is friction, and although we often think of it as the annoying force that slows things down, wears objects out, or makes machines less efficient, it is also one of the reasons motion can become heat. Without friction, your shoes would not grip the ground, your car could not brake properly, a match would not ignite by striking a rough surface, and your hands would not warm when rubbed together. Friction begins with a truth that your eyes usually miss. Surfaces are not truly smooth. Even polished metal, smooth glass, or clean plastic, when seen at a microscopic level, has tiny hills, valleys, scratches, bumps, and irregularities. When two surfaces touch, they do not meet perfectly across their whole visible area. They touch at countless small high points. As one surface slides over another, those tiny contact points catch, deform, break, and reform. The materials resist the sliding motion, and the energy you put into moving them has to go somewhere. Some of it may become sound, like the squeak of shoes on a floor. Some may cause wear, tearing away tiny particles. Some may slightly deform the surfaces. But much of it becomes internal energy, which means the atoms and molecules in the materials jiggle more intensely. And that increased microscopic motion is what we feel as heat. So, when your hands warm up, they are not being heated by a hidden flame. The movement of your muscles is being converted into faster molecular motion in your skin. The same principle appears when a rope slides quickly through your hands and burns your palms. When a drill bit grows hot as it cuts into wood or metal. When bicycle brakes heat up on a long downhill ride, or when car brakes convert the motion of a vehicle into heat in the brake pads and rotors. Braking is one of the clearest examples. A moving car has a great deal of kinetic energy, the energy of motion. When the driver presses the brake pedal, brake pads press against spinning metal discs or drums. Friction resists the rotation, slowing the wheels, but the energy does not vanish. It becomes heat. That is why brakes can become dangerously hot if used too hard for too long, especially on steep roads. In extreme cases, overheated brakes can lose effectiveness because the materials may no longer behave as designed. Here, friction is both protector and risk. It allows control, but it demands respect. The same hidden exchange happens when a meteor enters Earth's atmosphere, though the common phrase "burning from friction" is only partly the story. The intense heating comes largely from the air in front of the meteor being compressed and shocked as the object moves at enormous speed, along with interactions with the surrounding air. Friction like drag matters, but it is not simply the meteor rubbing against air like hands rubbing together. This distinction is important because real physics is often more interesting than the shortcut version. Motion through matter can create heat in more than one way. Sliding contact, deformation, compression, turbulence, and drag can all turn organized motion into disordered molecular motion. That word organized matters. When an object moves, its atoms are all, in a broad sense, traveling together in the same direction. But heat is different. Heat is not a single clean movement. It is microscopic disorder, atoms vibrating, rotating, colliding, and shifting in countless directions. Friction takes smooth, directed motion and spreads it into small random motions inside materials. It is like turning a clear melody into a room full of murmurs. The energy is still there, but it is no longer arranged in a way that easily moves the object forward. That is why friction feels like loss in machines. A machine is usually designed to channel energy into useful motion, but friction leaks some of that energy into heat. This is why engines need oil, why gears are lubricated, why bearings exist, and why engineers work so hard to reduce unnecessary friction. Oil or grease creates a thin layer between surfaces, helping them slide without as much direct contact between microscopic rough spots. Bearings replace sliding with rolling, which often wastes less energy. Smooth coatings, careful materials, and precise designs all try to control how much motion becomes unwanted heat. Yet friction is not the enemy of technology. It is a tool when we need grip, stopping power, traction, or ignition. A match lights because the striking surface and match head create heat and help start a chemical reaction. Tires grip the road because friction lets rubber push against pavement. Your fingers hold a cup because friction prevents it from slipping. Even writing with a pencil depends on friction pulling tiny bits of graphite onto the paper. Life in a frictionless world would not be elegant. It would be helpless. You could not walk normally, pick things up securely, or stop moving once you started. Every step you take is a negotiation with friction, and every stop is motion being quietly transformed. There is also a deeper lesson in the way friction creates heat. It shows that resistance is not always empty opposition. Sometimes resistance is the place where transformation happens. Without resistance, motion continues, but nothing changes form. With resistance, energy is redistributed. A spinning wheel slows and warms. A hand rubs and glows with heat. A tool cuts and heats its own edge. A brake pad sacrifices coolness to create safety. The warmth is the record of motion meeting opposition. And if you listen closely, friction is always telling you that the physical world keeps accounts. Energy may become harder to use, more spread out, less organized, but it is not simply erased. It migrates into vibrations, heat, sound, wear, and tiny structural changes. That is why a moving object can slow down while the universe does not lose what the motion carried. It only changes the language in which that energy is written. So the next time you rub your hands together on a cold morning, or feel a tire warm after a long drive, or smell the sharp trace of a match just struck, do not see only a familiar sensation. See motion being translated into warmth. See microscopic roughness turning, sliding into vibration. See surfaces catching, releasing, deforming, and sharing energy in ways too small for the eye, but large enough for the skin to feel. Friction may seem ordinary because it surrounds every movement of your life, but beneath it is one of the most important truths in physics. The world does not let motion disappear quietly. It turns it into heat, into sound, into change, into the hidden trembling of matter. And in that simple warmth between your palms, you can feel the universe reminding you that every movement leaves a trace. Cracks follow hidden stress patterns. A crack is not a random line of damage. It is a secret map of where a material could no longer carry the invisible weight placed inside it. You see a broken phone screen, a dry lake bed, a chipped ceramic plate, a wall with a thin fracture running through the paint, and it may look like disorder, like something simply failed and split wherever it happened to be weakest. But cracks usually do not wander without reason. They follow hidden stress patterns, tracing the places where forces have gathered, stretched, squeezed, twisted, or concentrated until the material's internal bonds can no longer hold together. Before a crack appears, the surface may look calm. A pane of glass can seem perfectly still. A bridge beam can look solid. A rock can sit for years under pressure without changing shape in any obvious way. But inside, stress can be building like a silent weather system. Stress is not a visible substance. It is the internal force distributed through a material when that material is loaded, pulled, bent, heated unevenly, dried, cooled, struck, or restrained. As long as the material can spread that stress safely, nothing dramatic happens. But if the stress becomes too intense in one region, especially around a tiny flaw, scratch, pore, notch, corner, or impurity, that region becomes a starting point. The material does not need to be weak everywhere. It only needs one place where the local stress becomes strong enough to open a path. That is why cracks often begin at sharp corners or scratches. A smooth curve spreads force more gently, but a sharp point concentrates it. It is like a crowd moving through a wide hallway and then being forced through a narrow door. The pressure gathers at the bottleneck. In materials, this concentration can make a tiny defect more dangerous than it looks. A microscopic flaw that your eyes cannot see can become the seed of a visible fracture. Once the crack begins, the tip of the crack becomes even more important because stress gathers strongly at that sharp tip. The crack tip is like a moving front line where bonds are being asked a question. Can you hold or must you separate? If the force driving the crack is strong enough, the crack grows. If not, it may stop, pause, or remain harmless for years. This is why engineers care so deeply about crack growth. A small crack is not always immediate failure, but it is a warning that must be understood. In airplanes, bridges, pressure vessels, ships, pipelines, and machinery, tiny cracks can grow slowly under repeated loading, a process called fatigue. Each cycle of stress may be too small to break the object at once, but over thousands or millions of cycles, the crack can extend little by little, like a sentence being written one nearly invisible letter at a time. This is why inspections matter. The danger is not only the force you apply today, but the history of forces the material has already lived through. A metal part can survive one load, then another, until a hidden crack reaches a critical size and failure happens suddenly. To the eye, the break may seem instant. To the material, it may have been preparing for a long time. Cracks also reveal how materials differ. Glass and ceramics are brittle, so once a crack starts, it can race quickly because the material cannot easily deform to blunt the crack tip. Metals, depending on the type and condition, can often stretch and deform before breaking, which can absorb energy and slow crack growth. That is one reason metals may bend before they fail, while glass may shatter with little warning. Concrete behaves differently again. It is strong in compression, but weak in tension. So cracks often form where pulling forces appear, and steel reinforcement is added to carry those tensile loads. Wood cracks along grain because its internal structure has direction. It is easier for a split to follow the fibers than to cut across them. Dry mud cracks because water leaves, the material shrinks, and the surface is restrained by the layer beneath it, creating tension that breaks the drying surface into patterns. Paint cracks when layers expand, shrink, age, or fail to stick together evenly. Even a cracked sidewalk can tell a story about heat, cold, roots, settling ground, and the weight of time. The crack is the visible result, but the cause is often a hidden conversation between material, environment, and force. Sometimes cracks branch, sometimes they curve, sometimes they stop at holes or edges, sometimes they form repeating polygon shapes. These patterns are not artistic choices. They reflect how stress moves and redistributes. When one crack opens, it releases stress nearby, which can guide where the next crack forms. In drying mud, for example, one crack can relieve tension along its path, causing later cracks to meet it at angles rather than simply crossing at random. In glass, fast-moving cracks can branch because the energy driving the crack becomes too much for one path to carry smoothly, so the fracture splits into multiple paths. In toughened glass, built-in surface compression can make the glass stronger against small damage, but when it finally fails, it can break into many small pieces rather than long, sharp shards. That behavior is engineered, not accidental. It shows that even breaking can be designed. Humans cannot stop materials from obeying stress, but we can shape how stress is distributed, where cracks are likely to begin, and how damage spreads if it occurs. This is why aircraft windows have rounded corners, not sharp square ones. It is why engineers avoid abrupt changes in shape where stress can concentrate. It is why holes may be drilled at the ends of cracks in some repairs, not to make the crack disappear, but to blunt the sharp tip and reduce the concentration that helps it grow. It is why bridges, bones, tools, buildings, and engines are designed with the understanding that failure often begins small. A crack teaches that the weakest place is not always the thinnest place, or the oldest place, or the place that looks most damaged. It is the place where stress, structure, and flaw meet in the wrong way. And this makes cracks strangely honest. They do not flatter the surface. They reveal where the internal story became unsustainable. A wall may look smooth until a line appears. A plate may seem whole until a tiny chip becomes the path of a split. A rock face may stand for centuries until water enters small fractures, freezes, expands, and widens them season after season. The crack is not only destruction, it is information. Geologists read fractures in rock to understand pressure, movement, cooling, earthquakes, and ancient stress in the Earth's crust. Materials scientists examine broken surfaces to learn how and why something failed. Engineers study fracture surfaces under microscopes because the broken edge can contain clues. Slow fatigue marks, sudden brittle failure, stretching before fracture, corrosion, overheating, or repeated impact. Even failure leaves evidence if you know how to look. There is something quietly unsettling in this, because cracks remind you that what appears solid may be carrying invisible tension all the time. A structure can look unchanged while forces rearrange themselves inside it. A small flaw can matter more than a large surface. A line can appear suddenly, but its cause may be old. And yet, this is not a message of fear. It is a message of attention. Cracks show us that materials have limits, but also that limits can be studied, respected, and designed around. They are not meaningless scars. They are the handwriting of stress. They tell us where force traveled, where resistance ended, where energy found a path through matter. So the next time you see a crack in ice, glass, stone, paint, clay, or concrete, do not see only damage. See a hidden map made visible. See a tiny defect amplified by pressure. See a material revealing the direction of forces it could no longer hide. And let it ask you, gently, how many things in the world seem calm only because the stress inside them has not yet found its line. Snowflakes rarely repeat exactly. Every snowflake is a tiny record of a journey no other snowflake has taken in exactly the same way. It begins high above you, not as a perfect star, not as a delicate ornament, but as a nearly invisible speck in a cold cloud. A tiny dust particle, a grain of pollen, a microscopic fragment of sea salt, or another small surface where water vapor can begin to gather. In the open air, water vapor does not always become ice just because the temperature is low. It often needs something to cling to, a starting point, a seed, a place where molecules can settle and begin arranging themselves. Around that tiny nucleus, water molecules from the surrounding vapor attach one by one, and because of the way water molecules bond when they freeze, the growing crystal naturally tends towards six-sided symmetry. That six-fold pattern is not an artistic accident. It comes from the molecular structure of ice, from the angles and arrangements that water molecules prefer when they lock into a frozen lattice. So the snowflake's beauty begins with a rule. Ice grows with a hidden geometry inside it. But the reason snowflakes rarely repeat exactly is that the rule is only the beginning, not the whole story. As the young ice crystal drifts through the cloud, it passes through tiny changes in temperature, humidity, air movement, and water vapor concentration. A little colder here, slightly warmer there, wetter air in one region, drier air in another, a gentle upward current, a slow fall, a brief spin, a moment inside a pocket of cloud where vapor is abundant, then a quieter region where growth slows. Each small change affects how the crystal grows. Sometimes the corners grow faster, sometimes flat plates form, sometimes branches stretch outward, sometimes side branches sprout from larger arms, sometimes a column-like shape appears instead of a flat star. The snowflake is not stamped from a mold. It is grown by conditions. Its form is a history of the air it moved through. This is why two snowflakes can look similar, especially if they grow in similar clouds. But the chance of two complex natural snowflakes matching in every microscopic detail is extraordinarily small. To repeat exactly, they would need to experience the same starting point, the same temperature changes, the same humidity changes, the same path through the cloud, the same collisions or lack of collisions, the same timing of every molecule that joined the crystal, and the same tiny imperfections along the way. Nature does not usually replay a journey with that level of precision, and yet, snowflakes often look balanced, because all the arms of one snowflake grow close together in the same local conditions at the same time. If one part of the cloud favors branching, every arm of that same flake may receive a similar instruction from the surrounding air. This is why a single snowflake can appear beautifully symmetrical while still being unique. Its arms are like siblings growing in the same weather, shaped by the same atmosphere, but not always perfectly identical. If you look closely at real snowflakes under a microscope, you often find irregularities. One branch shorter, one edge rougher, one side damaged, one detail missing. The perfect snowflake in drawings is an idealization. Real snowflakes are more alive-looking, more weathered, more personal. They may collide with other ice crystals, break, melt slightly, refreeze, collect tiny droplets that freeze onto them, or become clumps rather than isolated stars. Some snow falls as simple plates, needles, columns, capped columns, dendrites, or irregular crystals. The classic six-branch star is only one kind, and it forms only under certain conditions. Temperature and humidity are especially important. At some temperatures, ice tends to grow into thin plates. At others, it may grow into columns. Under conditions where the air contains a lot of water vapor, branching becomes more dramatic, because corners and edges can collect vapor efficiently and grow outward quickly. Once a branch sticks out slightly, it has access to more vapor than a flatter region, so it can grow even more. And that small advantage becomes amplified into the feathery arms you recognize as a snowflake. This is an example of how complexity can arise from simple rules repeated in changing conditions. No one designs every branch. No tiny sculptor carves each point. The pattern emerges because molecules follow local physical laws, and those local choices accumulate into a shape that feels almost intentional. That is what makes snowflakes so powerful as a symbol, but also so important as science. They teach you that order does not always require a planner. Sometimes order grows from constraints. The water molecule has a shape. The ice lattice has a structure. The cloud has temperature and humidity. The falling crystal has a path. From these ingredients, beauty appears. Not guaranteed beauty, not perfect beauty, but patterned beauty. And when you understand this, a snowflake becomes less like a decoration and more like a frozen diary. Its branches record the invisible atmosphere, where the air was moist enough to feed rapid growth, where the temperature encouraged flat spreading, where a small edge became a growing tip, where the crystal was interrupted, where its balance was preserved, where its journey changed. You cannot read every detail easily with the naked eye, but the information is there, written in ice. Scientists who study snow crystals can recreate many snowflake forms in controlled chambers by adjusting temperature and humidity, showing that these shapes are not random miracles. They are reproducible patterns under particular conditions. But reproducible does not mean every flake becomes identical. It means the same kind of environment can produce the same family of shapes. Two trees can both be oaks and still have different branches. Two fingerprints can both be human and still be distinct. Two snowflakes can both be stellar dendrites and still carry different microscopic histories. This is where the famous phrase, "no two snowflakes are alike," needs careful handling. For simple crystals, especially very tiny ones with few features, two may be extremely similar, perhaps close enough that you could not tell them apart with ordinary tools. But for large, complex natural snowflakes with many branches and details, exact repetition is so unlikely that the phrase captures a real truth about complexity. The more steps involved in forming something, the more chances there are for small differences to enter. A snowflake's uniqueness is not magic. It is statistics plus history plus environmental sensitivity. It is the result of many tiny decisions made by physics, and there is something deeply calming in that. The snowflake does not rush. It grows by receiving what the air gives it. It becomes what conditions allow. It carries symmetry but also accident. It is shaped by rules but never reduced to a copy. For a few minutes or hours, it exists as a fragile architecture of ice, and then it falls into a warmer world where it may melt on a sleeve, vanish on a window, join a snowbank, or become part of water again. Its uniqueness does not make it permanent. In fact, its beauty is sharpened by how temporary it is. A snowflake is precise but brief, individual but fragile, patterned but never fully predictable. And maybe that is why snow can make the world feel quiet in a way rain does not. Each flake falls softly, carrying an entire cloud history in a shape too small to hold for long. You see a white blanket covering the ground and think of sameness. But that sameness is made from countless differences layered together. From far away, snow looks like one thing. Up close, it is a crowd of unique structures, each one shaped by a path through air that cannot be exactly repeated. That contrast is worth holding in your mind. Many things in life look uniform from a distance. A forest looks like a green mass until you see each leaf. A city looks like lights until you imagine each window. Snow looks like whiteness until you remember every flake has its own formation story. Science does not remove the wonder from that. It deepens it. It tells you that the six-fold star is written by molecular geometry, that the branching is guided by humidity and temperature, that the uniqueness comes from motion through a changing cloud, and that the softness on your glove is a physical history made visible. So the next time snow begins to fall, do not see only weather. See billions of tiny experiments descending at once. See water vapor becoming architecture. See clouds writing in ice, each letter similar, none exactly the same. And let that quiet fact stay with you. The world can repeat its rules endlessly without repeating its results exactly. The same laws, the same molecule, the same cold sky. And still each snowflake arrives as a small original answer. Not because nature is trying to be poetic, but because reality is sensitive, layered, and alive with conditions. A snowflake rarely repeats exactly because no journey through the atmosphere repeats exactly. And in that gentle falling proof, you can feel one of the deepest truths of the ordinary world. Even when everything seems familiar, the details are still being born for the first time. Ice floats because water expands when frozen. The most important thing ice does may not be that it becomes cold and hard, but that it refuses to sink. You drop an ice cube into a glass, and it rises to the top so naturally that it feels unworthy of wonder. Yet this small floating cube is one of the reasons Earth is livable. Most substances become denser when they freeze. Their particles slow down, settle into tighter arrangements, and pack more closely together, so the solid form usually sinks in the liquid form. But water behaves differently. As liquid water cools, it does become denser for a while, reaching its greatest density at about 4 degrees Celsius. Then, as it cools further toward freezing, something unusual begins to happen. The water molecules start arranging themselves into a more open structure, held by hydrogen bonds, and when the liquid becomes solid ice, those molecules lock into a pattern that leaves more empty space between them than liquid water has. So ice takes up more volume than the same amount of liquid water. It expands as it freezes, becomes less dense and floats. That may sound like a small detail, but it changes entire worlds. If ice sank, winter would be far more dangerous for lakes, ponds, and rivers. The surface water would freeze, sink, and expose new water to the cold air. That new water would freeze and sink too. Over time, a lake could freeze from the bottom upward, turning into a block of ice much more easily and threatening nearly everything living inside it. But because ice floats, it forms a layer on top. That floating ice becomes a kind of cold shield. It separates the water below from the freezing air above and slows further heat loss. Because ice is not a perfect conductor of heat. Under the ice, liquid water can remain, often cold but still fluid, allowing fish, insects, microorganisms, and plants to survive through winter. In this sense, floating ice is not just a curiosity, it is a seasonal shelter. The frozen surface looks like stillness, but beneath it life continues in a dark, slow, protected world. Water's density behavior adds another layer to this. Since liquid water is densest around 4 degrees Celsius, that denser water tends to sink in cold seasons, while colder water near freezing stays closer to the surface and can become ice. This helps create a stable winter structure in lakes, ice above, near freezing water beneath it, and slightly warmer dense water deeper down. In spring and autumn, as temperatures change, lakes can mix in a process called turnover, bringing oxygen and nutrients through the water column. So water's strange density curve is not just about floating ice. It helps shape the rhythm of aquatic ecosystems. A lake is not simply a bowl of water waiting for weather to act on it. It is a layered breathing system, guided by the unusual physics of the molecule filling it. The reason this happens comes from water's shape and electrical nature. Each water molecule is made of 1 oxygen atom and 2 hydrogen atoms arranged at an angle. Because oxygen pulls electrons more strongly than hydrogen, the molecule has a slightly negative side and slightly positive sides. This makes water molecules attract one another through hydrogen bonds. In liquid water, these bonds are constantly forming and breaking, allowing molecules to move around while staying connected in a flexible network. But when water freezes, the molecules settle into a more orderly structure, where hydrogen bonds hold them apart in a spacious arrangement. The solid becomes rigid but not tightly packed. That is the paradox. Freezing makes water more ordered, yet less dense. The molecules become more disciplined, but they also stand farther apart. And from that open microscopic architecture comes the visible fact that ice floats in your drink. This expansion also explains why freezing water can be so destructive. A bottle filled completely with water can crack in a freezer because the water needs more space as it turns into ice. Pipes can burst in cold weather when trapped water freezes and expands, creating pressure the pipe cannot handle. Rocks can split when water seeps into small cracks, freezes, expands, and pushes the crack wider. Over many cycles of freezing and thawing, this process, called frost wedging, can help break down mountainsides, roads, walls, and stone. The same property that protects lake life can damage buildings and reshape landscapes. Water is gentle enough to drink, but when it freezes in a confined space, it can become a powerful force. This is one of the quiet lessons of phase changes. A substance does not need to be violent in appearance to transform its surroundings. It only needs to change volume where the world is not ready to give it room. Ice floating also shapes climate. Sea ice, which forms from ocean water, floats on the ocean surface and reflects a great deal of sunlight back into space, because it is bright compared with darker ocean water. This reflectivity, called albedo, helps keep polar regions cooler. But sea ice is not exactly the same as a frozen lake surface. When seawater freezes, much of the salt is pushed out of the forming ice, making the ice less salty than the original water and leaving behind saltier, denser brine that can sink and influence ocean circulation. So again, floating ice is not an isolated fact. It connects to climate, ocean movement, ecosystems, and the planet's energy balance. When floating ice melts, the darker ocean beneath can absorb more sunlight, which can lead to more warming and more melting. The simple fact that ice floats becomes part of a much larger feedback system. And yet, the everyday version remains just as powerful. Look at an ice cube in a glass. It is not floating because it is lighter in the casual sense of being less material. It floats because the same mass of water has spread into a larger volume as it froze, lowering its density compared with the liquid around it. If you could shrink yourself down to the scale of molecules, you would not see a packed wall of frozen particles pressed tightly together. You would see an open structure, a quiet framework of bonds, a solid with space built into it. That hidden space is what lifts the ice. It is strange to realize that emptiness inside structure can decide whether something sinks or floats. Whether a lake seals itself from winter or freezes deeper, whether a fish survives until spring, whether a pipe breaks in a wall, whether a rock slowly fractures over years. Water's expansion on freezing is not an exception tucked away in a textbook. It is one of the background conditions of life on Earth. It is part of why winter is survivable in freshwater habitats. It is part of why landscapes weather and change. It is part of why icebergs float with most of their mass hidden below the surface, reminding you that what you see above water is only a fraction of the whole. And maybe that is why this fact deserves to be felt, not just known. Ice floats because water, at the moment it becomes solid, opens itself into a wider structure. It becomes rigid but less crowded. It becomes colder but more spacious. It becomes still, yet it protects motion beneath it. There is something quietly beautiful in that contradiction. The frozen layer that looks like an ending can become a roof over life. The expansion that breaks stone can shelter a lake. The cube in your glass, ordinary and clear, carries a rule strange enough to shape planets. So the next time you see ice drifting on water, do not pass over it too quickly. See the molecular architecture holding it up. See the open spaces inside the solid. See winter placing a lid on a lake instead of a weight at its bottom. See life waiting below, slowed but not erased. And let this small floating thing remind you that the world's most important miracles are often not loud at all. Sometimes they rest quietly at the surface, cold, transparent, and familiar, preserving the depths because water expands when it freezes. Lightning creates powerful chemical reactions. A lightning bolt is not just a flash of electricity in the sky. It is a chemical factory that opens for a fraction of a second and rewrites the air it cuts through. You see the light first, a white vein across the storm, then hear the thunder arrive like the sky remembering what happened. And it is easy to think the event is only brightness, heat, danger, and sound. But inside that sudden channel, the air is being forced into reactions it would almost never perform under ordinary conditions. The atmosphere around you is mostly nitrogen and oxygen, and both are familiar enough to feel passive, like background ingredients you breathe without noticing. Nitrogen especially seems quiet because nitrogen molecules are extremely stable. They are held together so tightly that most living things cannot use nitrogen gas directly, even though nitrogen is essential for building proteins, DNA, and the chemistry of life. Plants need nitrogen in more reactive forms, such as nitrates or ammonium. But the air is full of nitrogen, locked in a form that is difficult to break open. Then lightning arrives. In the narrow path of a bolt, temperatures can briefly become hotter than the surface of the sun, and that extreme energy tears apart nitrogen and oxygen molecules in the air. Once those strong bonds are broken, the freed atoms can recombine in new ways, forming nitrogen oxides, often called NOx. These molecules are chemically active, not sleepy like ordinary nitrogen gas. As the storm continues, they can react further with oxygen, water vapor, and other atmospheric chemicals, eventually helping form nitric acid and nitrate particles that can dissolve in raindrops and fall to the ground. In simple terms, lightning can take nitrogen from the air, force it into a more useful chemical form, and deliver some of it to soil through rain. This is one form of natural nitrogen fixation, and although bacteria are the great long-term masters of nitrogen fixation on Earth, lightning still plays a real role in the global nitrogen cycle. It is not feeding every forest by itself, and it is not replacing the work of microbes, but it contributes a dramatic, skyborne source of reactive nitrogen. Every storm in this sense is not only weather, it is chemistry descending. The rain after lightning can carry traces of nitrates that plants may eventually use, turning a violent moment in the atmosphere into part of the quiet growth of leaves, roots, and fields. The same bolt that can split a tree can also help make nutrients. That contrast is what makes lightning so strange. It is destructive at one scale and creative at another. It breaks bonds so new bonds can form. It tears the air open and leaves behind molecules that enter cycles of life. Lightning also creates ozone. High-energy electrical discharge can split oxygen molecules, and some free oxygen atoms can join with oxygen molecules to form ozone, a molecule made of 3 oxygen atoms. Near the ground, ozone is not something you want in large amounts because it can irritate lungs and damage tissues. High above Earth, in the stratosphere, ozone helps absorb harmful ultraviolet radiation from the sun, but close to the surface, it is a reactive pollutant when concentrated. After a storm, people sometimes say they smell ozone, that sharp, clean scent in the air, though the smell after rain is not only ozone. It can also include petrichor, the earthy smell released when rain hits dry soil, partly from compounds made by soil microbes. Real storms are mixtures of chemistry, dust, moisture, plants, soil, and electricity, not one simple fragrance. Still, lightning can produce ozone locally, and it also produces nitrogen oxides that influence atmospheric chemistry. These nitrogen oxides can help form or destroy ozone depending on altitude, sunlight, and surrounding conditions. That is why lightning is important, not just for spectacular photographs, but for climate and air chemistry models. Storms are not chemical blanks. They inject reactive substances into the atmosphere, especially in regions where thunderstorms are frequent. Some lightning happens inside clouds, some between clouds, some from cloud to ground, and each kind can alter the chemical environment around it. The bolt lasts only a blink, but its products may enter chains of reactions that continue long after the sky has gone dark again. This is one of the deepest lessons of lightning. An event can be brief and still chemically meaningful. Duration is not the only measure of importance. Intensity matters, conditions matter. A fraction of a second at extreme temperature can do what years of calm air cannot. There is another layer to the story hidden in the way lightning makes thunder. The bolt heats the surrounding air so rapidly that the air expands violently, creating the shockwave you hear as thunder. That violent heating and cooling is also part of why unusual chemistry happens. Molecules are broken apart in the hot channel. Then, as the air cools, they recombine into new compounds before returning to the ordinary atmosphere. The storm becomes a forge, but unlike a metal forge with a steady flame, this one appears and disappears almost instantly, leaving chemical traces instead of a shaped tool. And lightning does not only act in the air. When it strikes sand, soil, or rock, it can melt minerals and sometimes create glassy structures known as fulgurites, which are like fossilized lightning paths through the ground. That is more geological than atmospheric, but it reminds you that lightning can alter matter wherever its energy is deposited. It can scorch bark, start fires, melt grains, split molecules, and change the chemistry of rain. In the early Earth, lightning may also have mattered in prebiotic chemistry. Experiments inspired by early atmosphere conditions, such as the famous spark discharge experiments, showed that electrical energy can help produce organic molecules from simple gases under certain mixtures. That does not mean lightning alone created life, and scientists still debate the exact conditions of early Earth's atmosphere and the pathways to life. But the basic principle is real. Electrical energy can drive chemical reactions that would not easily happen otherwise. Lightning is nature's reminder that chemistry often needs a push, a spark, a moment when stable molecules are forced out of comfort and into possibility. The air above you may seem empty, but it is filled with locked potential. Nitrogen, oxygen, water vapor, carbon dioxide, tiny particles, traces of gases, all of them are present in a restless but usually restrained mixture. Lightning changes the rules by injecting energy violently and locally. It does not create something from nothing. It rearranges what is already there. And perhaps that is why it feels so ancient, so mythic, and yet so scientifically precise. Long before humans understood chemical bonds, storms were already fixing nitrogen. Long before laboratories used electric discharges to study reactions, clouds were already running their own experiments. Long before agriculture depended on fertilizers, rainstorms were carrying small amounts of lightning-made nitrate into the soil. The sky was never just above life. It was participating in life's chemistry. When you watch a storm from a window, you are seeing more than a dramatic performance of light. You are seeing the atmosphere briefly become reactive, seeing stable molecules forced into new identities, seeing invisible nitrogen enter pathways that may one day pass through grass, insects, animals, and maybe even you. The flash is gone almost immediately, but the chemistry it begins can continue in rainwater, soil, roots, leaves, and food webs. That is the quiet wonder hidden inside the violence. Lightning looks like an ending, a rupture, a strike, but chemically, it can also be a beginning. It takes the ordinary air, the thing you forget because it is always around you, and proves that even it is full of sleeping transformations. So the next time thunder rolls after a bright fracture in the clouds, do not hear only noise. Hear the atmosphere being shaken into reaction. See the bolt not only as electricity, but as a brief furnace of molecular change. Imagine nitrogen bonds breaking, oxygen rearranging, ozone forming, nitrates waiting to fall with rain. And let the storm ask you something gentle and unsettling. How many parts of the ordinary world are waiting for the right energy to become something entirely new? Resonance can break glass under the right conditions. A glass does not break because sound is loud. It breaks because the right vibration keeps arriving at exactly the right time. Imagine a wine glass sitting calmly on a table looking fragile but still complete. Its rim thin, its bowl curved, its structure quietly waiting. If you tap it gently with a fingernail, it sings. That small ringing note is not random. It is the glass revealing one of its natural frequencies, one of the ways it prefers to vibrate when disturbed. Every object has preferred patterns of motion like this. A swing moves most easily at a certain rhythm. A guitar string hums at certain notes. A bridge, a building, a bell, a window pane. Even the air inside a bottle can respond more strongly to some frequencies than to others. Resonance happens when an outside vibration matches one of those natural rhythms and keeps feeding energy into the system in step with its motion. A single push may not do much. A badly timed push may even fight the motion. But a perfectly timed push, repeated again and again, can make the motion grow. That is why a child on a swing can rise higher with small pushes, as long as each push arrives at the right moment. The energy does not need to be enormous all at once. It needs to be synchronized. A glass can break under the right conditions for the same reason. When a sound wave reaches the glass, it creates tiny pressure changes in the air around it. Those pressure changes push and pull on the glass surface. Usually the effect is too small to matter. Most sounds in a room simply pass by, reflect, fade, or make the glass vibrate so weakly you never notice. But if the sound matches the glass's resonant frequency, the glass begins to vibrate more strongly. The rim may flex in and out. The bowl may subtly change shape thousands of times per second. And if the sound continues with enough intensity and precision, the vibration can grow until the stress inside the glass becomes too great. At that point, a tiny flaw, scratch, bubble, or weak spot can become the starting point of failure, and the glass can crack or shatter. This is the real science behind the famous image of a singer breaking a wine glass with their voice. It is possible, but it is not easy, and it does not happen simply because someone sings dramatically. The singer must produce a note very close to the glass's resonant frequency, sustain it steadily, and make it loud enough for the glass to vibrate with large amplitude. The glass also matters. Thin crystal glasses are more likely to respond strongly because they can be lighter, more flexible, and less damped than thick, sturdy glass. A heavy drinking glass may absorb and dissipate the energy too quickly, or require far more sound power than a human voice can deliver. Some demonstrations use amplified sound or speakers because they can hold the exact frequency and volume more reliably than a voice alone. The glass may also break more easily if it has microscopic defects, because real materials are never perfectly smooth or flawless. A glass can look pure and transparent while hiding tiny weaknesses that decide where the break begins. This is important because resonance does not create damage from nothing. It increases motion. That motion creates stress. The stress finds the weakest path. So the shattering moment is not just sound winning against glass. It is a partnership between frequency, energy, material shape, damping, and imperfection. Damping is the quiet enemy of resonance. It is the way a system loses vibrational energy to heat, internal friction, the surrounding air, or other forms of motion. If a glass is strongly damped, the vibration dies away quickly, and resonance cannot build very far. If it is weakly damped, each correctly timed sound wave adds a little more energy before the previous motion has faded and the vibration grows. This is why resonance can feel almost unfair. A small repeated input can become powerful if the system keeps storing it instead of losing it. The sound does not smash the glass like a hammer. It persuades the glass into moving with it, cycle after cycle, until the motion becomes too much for the material to survive. And this idea reaches far beyond glass. Engineers must think about resonance whenever they design machines, bridges, aircraft, towers, engines, musical instruments, and buildings. A bridge can sway dangerously if wind, footsteps, or mechanical forces feed energy into one of its natural modes. A machine part can shake itself apart if rotating components create vibrations at the wrong frequency. Tall buildings are designed to manage wind-driven motion, sometimes with tuned mass dampers, large internal systems that move in opposition to the building's sway and drain energy from it. Airplanes, turbines, car engines, washing machines, and hard drives all have to deal with resonance because repeated vibration can grow quietly until it becomes destructive. But resonance is not only dangerous, it is also useful and beautiful. Musical instruments depend on it. A violin body amplifies the vibration of strings. A drumhead resonates when struck. A flute uses resonant air columns. A radio receiver selects signals by responding strongly to certain frequencies. Medical imaging and spectroscopy use resonant behavior to reveal hidden information about matter. Resonance is not the villain. It is a principle of selective response. It tells you that systems do not answer all disturbances equally. They answer most strongly when the disturbance speaks in their own rhythm. That is why the wineglass feels so symbolic. It shows that strength is not only about resisting force in general. Sometimes the most dangerous force is the one that matches you too well. A random noise may do nothing, while a precise tone can build inside the object until it finds the limit. The glass is not broken by chaos, but by coherence. The sound keeps arriving in agreement with the glass's motion, and agreement becomes power. There is something quietly unsettling in that, because resonance suggests that the world is full of hidden preferences. Objects have rhythms you cannot see. Structures have modes they do not reveal until they are touched, struck, shaken, or sung to. A glass on a shelf seems still, but it carries possible motions inside its shape. The note is already there, waiting to be awakened. Tap it, and you hear a glimpse of the structure's private rhythm. Match it, feed it, sustain it, and the quiet object can become overwhelmed by its own amplified motion. This is why resonance feels almost like a secret conversation between the outside world and the inner design of matter. The sound asks, "Is this your rhythm?" If the answer is no, little happens. If the answer is yes, the object begins to answer more and more loudly, even if the answer is silent to the eye at first. The glass trembles. The stress grows. A flaw opens. The object fails. And in that failure, the hidden rhythm becomes visible for one violent instant. So when you hear that resonance can break glass, do not imagine sound as a magical weapon that destroys anything it touches. Imagine a more precise and more fascinating truth. Every object has ways it prefers to move, and under the right conditions, a repeating vibration can feed those motions until they become larger than the object can bear. A glass shatters not because sound is mysterious, but because matter is responsive. It has limits. It has internal patterns. It has weak points. It has rhythms. And perhaps that is the lesson resonance leaves behind. The world is not only made of shapes, it is made of possible motions hidden inside shapes. A quiet glass contains a note. A bridge contains a sway. A string contains a song. A building contains a slow breath of movement. Most of the time, these rhythms stay small, harmless, invisible. But when the right frequency arrives and keeps arriving, the ordinary object reveals that stillness was never the absence of motion. It was only motion waiting for the right invitation. Sand can flow like a liquid. Pour sand through your fingers, and it behaves like a liquid made from tiny stones. It slips downward in a narrow stream, fills the shape of a container, forms ripples, pours through an hourglass, spreads across a floor, and gathers into dunes that look almost like frozen waves. Yet the moment you step on a beach, that same sand can hold your weight like a solid ground. Push it into a castle, and it keeps a shape for a while. Bury your hand in it, and it resists. This double nature is what makes sand so quietly strange. It is not a liquid, but it can flow like one. It is not a solid block, but it can support weight. It is not a gas, but under certain conditions, it can behave like a restless cloud of grains. Sand belongs to a class of materials called granular matter, made of many separate solid pieces that interact through contact, friction, gravity, and collisions. Each grain is solid, but a pile of grains can behave in ways that no single grain could. That is the key. Sand's mystery is not in one particle alone. It is in the crowd. When grains are resting together, they form networks of contact, tiny chains of force running through the pile. Some grains press against others, those press against others, and the weight is carried through hidden paths. This is why a sand pile can stand in a sloping shape instead of spreading flat like water. The grains rub, lock and support each other, but tilt the pile too far, shake it, pour more sand on top, or disturb the contacts between grains, and the structure suddenly gives way. The grains begin to slide, tumble and roll over one another, and the pile flows. This is why dry sand naturally forms a cone when poured from above. It grows steeper until it reaches a certain stable slope, often called the angle of repose. Add more sand and small avalanches slide down the sides, restoring the slope. The pile is constantly negotiating between stability and motion. Too shallow and it rests. Too steep and it flows. In that simple cone is a lesson about mountains, dunes, landslides, and industrial materials. Sand does not need to melt to behave like a fluid. It only needs its grains to lose the contact arrangement that was holding them in place. In an hourglass, the grains fall through a narrow opening in a steady stream, but not exactly like water. Water flow depends strongly on pressure from the liquid above, while dry sand flowing through a small hole can have a rate that depends more on the opening size and grain behavior near the outlet. The grains form temporary arches, break apart, collide, and continue downward. If the opening is too small compared with the grains, the flow can jam. Suddenly the liquid stops, not because the grains have disappeared, but because a small self-supporting structure has formed at the bottleneck. This is one of the strange features of granular materials. They can flow smoothly one moment and clog the next. Anyone who has tried to pour sugar, salt, rice, or grain through a narrow funnel has seen this. A small tap can restart the flow by breaking the arch of particles. That tap is not adding much material. It is destroying a temporary structure. Sand can also behave more like a liquid when air or water moves through it. If air is blown upward through a bed of fine grains with enough strength, the grains can become fluidized, lifting slightly and moving around so that the whole bed behaves almost like a boiling liquid. Industrial systems use this effect in fluidized beds, where powders or grains are suspended by upward gas flow to improve mixing, heating, drying, or chemical reactions. The grains are still solid, but the group behaves like a fluid because the upward flow reduces the weight each grain effectively places on its neighbors. Contacts loosen, frictional locking weakens. The bed can bubble, swirl, and flow around objects. This is also why some sand can become dangerous during earthquakes. When wet, loose sand is shaken strongly. The water pressure between grains can rise, and the grains can lose their stable contact network. The ground may temporarily behave more like a liquid, a process called liquefaction. Buildings can tilt, roads can buckle, and buried structures can rise or sink, not because the sand literally turns into water, but because the grain skeleton that carried weight becomes weakened. The solid ground fails as a solid and begins to flow. Quicksand works through a related idea, though it is often exaggerated in movies. Real quicksand is usually a mixture of sand, water, clay, or other fine material, where the grains are loosely packed and the mixture cannot support weight in the usual way. You do not normally vanish instantly into it, but struggling can make movement harder because the mixture resists rapid motion and can trap legs by suction-like effects and grain rearrangement. The danger is usually not being swallowed whole, but becoming stuck, exhausted, or trapped in a changing environment like a tide zone. Again, the truth is more useful than the myth. Sand can act fluid-like when the contacts between grains are disrupted, especially with water, vibration, or air helping separate them. But when grains settle and lock together, they can become surprisingly strong. This is why walking on dry, loose sand feels tiring. Each step pushes grains aside, and your foot sinks because the sand flows away under pressure. Wet beach sand near the waterline can feel firmer because a small amount of water creates capillary bridges between grains, tiny liquid connections that help grains cling together. Too much water, however, fills the spaces and can make the sand softer again. This is why sandcastles need the right amount of moisture. Dry grains will not hold a tower. Completely soaked sand slumps. Slightly wet sand can stand because water creates cohesion between grains. A child building a sandcastle is unknowingly working with granular physics, surface forces, packing, and stability. Dunes reveal another side of the same science. Wind lifts and pushes sand grains, but it does not move every grain the same way. Some grains bounce along the surface, striking others and knocking them forward. Others creep. Over time, the wind builds dunes with smooth windward slopes and steeper slip faces where sand avalanches downward. A dune can migrate across a desert like a slow wave, not because the whole dune slides as one object, but because countless grains are lifted, moved, dropped, and buried again. The shape travels while the individual grains cycle through it. This is a beautiful reversal of how we usually think about objects. A dune seems like a thing, but it is more like a process with a shape. It exists because grains keep moving through a pattern. Sand also helps scientists think about crowds, traffic, powders, cereal, pills, landslides, and even asteroid surfaces. Granular matter appears in agriculture, construction, mining, pharmaceuticals, and food production. It is surprisingly difficult to predict because every grain touches other grains, and small changes in shape, size, moisture, roughness, and vibration can produce very different behavior. Perfect spheres flow differently from jagged grains. Fine powder can clump. Mixed grain sizes can separate when shaken, sometimes making larger pieces rise to the top, as in the Brazil nut effect in a container of mixed nuts. A pile can look stable while carrying stress through hidden force chains, then fail suddenly when one part shifts. This is why silos storing grain can collapse or clog in unexpected ways, and why engineers design hoppers carefully to prevent jams. Sand teaches that matter in crowds has its own personality. A single grain is simple. A million grains become complex. The group can pour, jam, avalanche, compact, loosen, support, collapse, or flow, depending on how it is treated. And there is something deeply reflective in that. Sand does not have the smooth continuity of water, yet from a distance it imitates water's gestures. It streams, waves, ripples, and settles. Up close, it is a society of separate pieces, each one hard, each one limited, each one touching and being touched. Its fluidity comes not from softness, but from collective motion. Its solidity comes not from one unbroken structure, but from temporary support between neighbors. In this way, sand feels like a quiet lesson in emergence. The behavior of the whole cannot be understood by staring at one grain alone. You have to watch the relationships. You have to see how contact becomes strength, how disturbance becomes flow, how pressure becomes jamming, how motion becomes pattern. So the next time you walk across a beach, pour sugar into a cup, watch an hourglass, or see wind push sand across a road, do not think of grains as simple debris. See them as a material living between categories. See each pile as a balance between rest and collapse. See each stream as solids behaving like a liquid without ever ceasing to be solid. Sand reminds you that the world is not always divided into neat states and simple labels. Sometimes, reality is made of countless small pieces that together become something with moods. Firm under one touch, flowing under another, stable for years, then moving all at once. And in that ordinary handful of grains, slipping quietly through your fingers, you can feel one of nature's most important truths. The behavior of a thing is not always hidden inside its parts alone, but in the way those parts meet, press, release, and move together. Fluids can form spirals, waves, and cells. A pot of soup warming on a stove can become a miniature planet, building hidden currents, rising towers, sinking lanes, rolling waves, and small repeating cells before your eyes even notice anything has begun. At first, a fluid looks like the opposite of structure. It spreads, pours, drips, swirls, and slips away from fixed form, so you might imagine it as shapeless matter, something that only takes the shape of its container and then waits. But fluids are not empty disorder. They are systems that can organize motion into patterns when energy flows through them. Heat them from below, cool them from above, spin them, shake them, push them past a surface, let one layer slide over another, or place two fluids of different density together. And suddenly the smoothness breaks into spirals, waves, rolls, fingers, plumes, and cells. The word fluid includes liquids and gases, which means this quiet pattern making is happening not only in water, oil and soup, but also in air, clouds, oceans, stars, and the atmosphere around your body. One of the clearest examples is convection. When a fluid is heated from below, the warmer part expands slightly and becomes less dense, so it tends to rise. Cooler fluid above is denser, so it tends to sink. At first, if the temperature difference is small, heat may simply spread through the fluid without large visible motion. But once the difference becomes strong enough, the fluid begins to move in organized loops. Warm regions rise, cool regions fall, and a pattern of circulation appears. In a shallow layer of fluid heated evenly from below, this can form convection cells, repeating regions where fluid rises in one area, spreads, cools, sinks in another area, and then moves back below. These are sometimes called Bénard's cells, and under the right conditions, they can look like a honeycomb or a field of little circulating compartments. No one is drawing the pattern from outside. The pattern emerges because the fluid is trying to move heat more efficiently. The still state can no longer carry energy away fast enough, so motion begins. That is the deeper lesson. Patterns in fluids often appear when a simple flow becomes unstable and reorganizes itself into a more effective way of transporting heat, momentum, or material. You can see a gentle version in a lava lamp, where warmed wax becomes buoyant, rises, cools, sinks, and repeats in slow, glowing blobs. You can see it in a heated pan, where oil may shimmer as temperature differences change its thickness and motion. You can see it in the atmosphere, where warm air rises from the ground, cools as it expands, and can build clouds. A cloud is not just a floating white object. It is often the visible part of an upward-moving air current, where water vapor condenses into droplets. The sky, in that sense, is full of fluid patterns made visible by moisture. Waves are another way fluids organize motion. A wave on water is not simply water traveling across the surface like a moving carpet. Individual water particles mostly move in looping or back and forth paths, while the wave shape travels forward. The pattern moves through the fluid, carrying energy, while the water itself does not have to travel the whole distance with the wave. This is why a floating leaf can bob as waves pass rather than being carried instantly to shore. Surface waves form because gravity pulls displaced water back down, while inertia carries motion onward, creating the rise and fall you recognize. Small ripples are shaped more by surface tension, while larger waves are shaped mostly by gravity and wind. In the ocean, wind gives energy to the surface. Small ripples grow, waves interact, and the sea becomes a moving archive of weather. But waves do not only live on surfaces. Fluids can have internal waves too, hidden between layers of different density, such as warm and cold layers in the ocean. These internal waves can be enormous, sometimes far larger than the waves you see on the surface, moving slowly through the deep and mixing nutrients, heat, and salt. The ocean can look calm above, while great waves travel invisibly inside it. That fact alone should change the way you imagine water. The surface is only the visible skin of a much deeper motion. Fluids also make spirals when rotation and flow interact. Stir coffee and you create a curved motion that organizes the liquid around a center. But larger spirals appear in the atmosphere because Earth rotates. Hurricanes, cyclones, and large weather systems are not simply air moving inward toward low pressure in straight lines. Because Earth is spinning, moving air is deflected, and the result can be a rotating storm system with curved bands, an eye, and a structure that grows by feeding on warm ocean water and moisture. The spiral is not just a beautiful satellite image. It is heat, pressure, humidity, rotation, and condensation coupled together into a giant engine. On a smaller scale, when cream is poured into coffee, you may see curling tendrils and folded streaks because two fluids with different temperature, density, or thickness are mixing. The shapes seem artistic, but they are produced by stretching and folding. Fluids mix not by instantly becoming uniform, but by pulling differences into thinner and thinner strands until diffusion can finish the work at small scales. This is why smoke, dye, milk, ink, and clouds often create filaments before they disappear. Mixing is a story of stretching. A drop of dye in water does not simply vanish. It is torn into long threads, curved sheets, and tiny wisps until the boundaries become too fine to see. Another family of patterns appears when one fluid slides past another at a different speed. Under the right conditions, the boundary between them can wrinkle into waves and curls. This is called shear instability, and it can appear in clouds as dramatic rolling shapes that look like breaking ocean waves in the sky. It can happen when fast-moving air flows over slower air below, causing the boundary to billow. Similar processes occur in oceans, planetary atmospheres, and even in astrophysical gases. Again, a smooth boundary becomes unstable, and the instability becomes a pattern. Fluids can also form fingers when a lighter fluid pushes into a heavier one, or when a less thick fluid pushes into a thicker one. Instead of advancing as a clean flat front, the invading fluid may split into branching shapes like roots or veins. You can see related patterns in oil recovery, in ink spreading through certain materials, in lava flows, in groundwater movement, and in laboratory plates where fluids are squeezed between close surfaces. The shape of motion depends on density, viscosity, speed, boundaries, and the forces acting within the fluid. Viscosity matters because it describes how strongly a fluid resists flowing. Honey resists motion more than water. Air resists far less than syrup. A thick fluid smooths out small disturbances. A thin one may allow faster, more intricate motion. But even very thin fluids can organize beautifully when the flow is right. The important thing is that fluids do not merely move. They respond. They respond to heat by rising and sinking, to gravity by forming waves, to rotation by curving, to boundaries by slowing near walls, to pressure differences by accelerating, and to instability by building new shapes. This is why fluid dynamics is so difficult and so essential. It governs weather prediction, ocean currents, blood flow, airplane design, engine cooling, climate, volcanic plumes, river deltas, cloud formation, and the way scents move through a room. When you smell coffee from across a kitchen, molecules are being carried by air currents that bend around objects, rise with warm air, and mix through invisible turbulence. When you watch steam above a cup, you are seeing warm, moist air rise, curl, cool, and fade as it mixes. When sunlight heats the ground, the air above it can shimmer because rising warm currents bend light differently than cooler surrounding air. The ordinary world is full of fluid patterns, but most of them pass too quickly, too gently, or too transparently for you to name. There is something quietly humbling about this. A fluid has no fixed shape, yet it creates shapes everywhere. It is soft, yet it can carve canyons over time, carry ships, break coastlines, lift birds, shape storms, and circulate heat around a planet. Its patterns are not permanent objects, but temporary agreements between motion and force. A convection cell exists only while heat keeps feeding it. A wave exists only while energy passes through. A spiral storm exists only while the atmosphere supplies moisture, rotation, and pressure differences. When the conditions fade, the pattern fades too. But while it lasts, it is real. It can move matter, change weather, transport life, and reshape land. This is the deeper beauty of fluids. They show that order does not always need rigid walls. Sometimes order is flow arranged by conditions. Sometimes shape is not something matter has, but something motion does. So the next time you watch tea swirl in a cup, clouds fold across the sky, oil shimmer in a pan, waves approach a shore, or steam rise from warm water, do not dismiss it as background movement. See a physical system searching for balance through motion. See heat becoming circulation, wind becoming waves, rotation becoming spirals, and instability becoming cells. The world is not still beneath its surfaces. It is constantly forming patterns that appear, evolve, and dissolve, teaching you that even shapeless things can become structured when energy passes through them. Fluids remind you that reality is often not a sculpture, but a dance. Not a fixed object held in place, but a moving pattern sustained for a little while by the forces that created it. Chaos can come from simple rules. A double pendulum begins with one simple swing, then suddenly moves as if the future has escaped prediction. At first, it seems like a toy made from logic. One arm attached to another, gravity pulling downward, joints allowing motion, energy moving back and forth. Nothing about it looks mysterious. There is no hidden motor, no random generator, no magical force. If you lift it and release it gently, you might expect it to repeat a graceful pattern forever, like an ordinary pendulum ticking in a clock. But give it just a little more energy. Change the starting angle by a tiny amount, and the motion can become wildly complex. It flips, hesitates, accelerates, reverses, loops over itself, and traces paths that look almost alive. This is one of the clearest doorways into chaos. The discovery that simple rules can produce behavior so complicated that long-term prediction becomes nearly impossible. Chaos does not mean anything can happen. It does not mean the universe has no laws. In science, chaos often means the opposite. A system follows definite rules, but those rules are so sensitive to starting conditions that even a tiny difference at the beginning can grow into a huge difference later. The double pendulum is not disobeying physics. It is obeying physics so precisely that every small detail matters. If you start it one way, it follows one path. If you start it almost the same way, so close that your eye cannot tell the difference, it may soon follow a completely different path. This is why chaotic systems are not simply random. Randomness is like rolling dice without knowing the result. Chaos is more unsettling because, in principle, the rules may be fully deterministic. Yet in practice, the future becomes hard to track because no measurement is infinitely perfect. You can never know the exact starting position, exact speed, exact air resistance, exact friction, exact tiny vibration from the table, exact state of every influence around the system. And in a chaotic system, those tiny uncertainties do not remain tiny, they grow. This is the meaning behind the famous butterfly effect, often described as a butterfly flapping its wings and eventually influencing a storm far away. The phrase is poetic, but the real idea is not that one butterfly literally controls the weather like a tiny god. The real idea is that in systems like the atmosphere, small differences can amplify through time, making long-range prediction extremely difficult. Weather obeys physical laws, but it is shaped by temperature, pressure, humidity, wind, sunlight, terrain, ocean currents, clouds, and countless interacting details. A tiny error in measuring today's atmosphere can grow until next week's forecast changes. This is why weather predictions are usually better for the near future than for far ahead. The atmosphere is not lawless. It is too richly connected. Chaos can also appear in dripping faucets. A single droplet forming at a tap seems simple. Water gathers, becomes heavy, falls, and another drop begins. At a slow, steady flow, the drops may fall in a regular rhythm. Increase the flow slightly, and the rhythm can change. Increase it again, and the pattern can become irregular. Not because the faucet has become conscious, but because the timing of each drop depends on the shape of the growing droplet, the motion left behind from the previous drop, surface forces, gravity, and small disturbances. A simple repeating process becomes a complex rhythm. You can find the same kind of sensitivity in population growth models, where a simple rule about reproduction can lead to stable numbers, repeating cycles, or chaotic fluctuations depending on how strongly the population responds to its own size. In ecology, a small change in food supply, predator numbers, disease, or climate can ripple through a system in ways that become difficult to predict. Again, chaos does not mean no pattern exists. Often, hidden within chaotic behavior is a deeper structure. Scientists call some of these structures strange attractors, patterns that chaotic systems tend to move around without repeating exactly. If you could draw the motion of certain chaotic systems in the right kind of abstract space, you might see a beautiful shape, not a straight line, not a simple circle, but a folded, layered form where the system keeps returning near previous states without ever tracing the exact same path. This is one of the strangest truths of chaos. Unpredictability can have shape. Disorder can have boundaries. A system can be impossible to forecast exactly for a long time and still follow a recognizable form of behavior. That is why chaos theory changed the way scientists think about nature. It showed that complexity does not always require complex rules. A few simple interactions, repeated again and again, can produce storms of behavior. The rule may be short. The result may be endless. Think of a coastline. From far above it looks jagged. Walk closer and smaller jagged edges appear. Look closer still, and the rocks, cracks and grains create more irregular detail. Nature often builds shapes that contain complexity at many scales. Chaos and related non-linear processes help explain why clouds billow, flames flicker, rivers branch, traffic suddenly jams, hearts can beat irregularly, and markets can shift unpredictably. Not all complexity is chaos, and not every irregular pattern is chaotic in the scientific sense. But chaos gives us a language for understanding how simple causes can generate surprising outcomes when feedback and sensitivity are involved. Feedback is one of the keys. In a simple linear system, pushing twice as hard may produce twice the effect. But in many real systems, effects loop back into causes. A small change alters the system. The altered system changes what happens next, and that next result changes the following result. Step after step, the difference grows, bends, folds, and multiplies. This is why chaos feels so alive. It is not a straight road. It is a maze that redraws itself as you move through it. But chaos is not only a challenge. It is also a source of creativity in nature. If everything were perfectly stable and predictable, the world would be rigid and lifeless. Chaotic mixing helps fluids blend. Irregular airflow shapes clouds and weather. Variable ecological dynamics can open space for adaptation. The brain itself operates with complex electrical activity that is not simply mechanical repetition. A healthy heartbeat is not perfectly like a metronome. It contains subtle variability. Too much order can be a sign of trouble, just as too much disorder can be dangerous. Life often lives between stiffness and chaos, between repetition and surprise. This balance is important because it teaches you not to treat unpredictability as failure. Sometimes unpredictability is a property of a system being deeply interconnected. You cannot always forecast exactly where a leaf will tumble in swirling air, but that does not mean the leaf is outside nature's laws. You cannot predict every detail of a storm weeks ahead, but the storm is still made of air, moisture, heat, pressure, and rotation obeying physics. You cannot know every future consequence of a small decision, but your life still unfolds through causes, responses, habits, and environments. Chaos reminds you that certainty has limits, not because reality is meaningless, but because reality is sensitive. It is shaped by beginnings too fine to measure and interactions too layered to hold completely in the mind. And perhaps that is the quiet emotional weight of this idea. You may want the world to be simple. One cause, one effect, one clear path from now to later. But many systems do not live that way. They begin with simple rules and become rich through repetition. A small difference becomes a large difference. A tiny tilt changes a path. A nearly identical beginning opens into another ending. This can feel frightening because it means control is never absolute. But it can also feel freeing because it means small things matter. A small correction, a small habit, a small kindness, a small shift in direction can grow over time in ways you cannot fully predict. Chaos does not promise that every small action becomes enormous, and it does not turn life into fantasy. It simply says that in sensitive systems, beginnings matter more than they appear to. So when you watch smoke curl, clouds gather, a pendulum tumble, water drip, traffic pulse, or weather change from calm to storm, do not see only disorder. See simple rules unfolding through feedback. See tiny differences being amplified. See a world where pattern and unpredictability are not enemies, but partners. Chaos is not the absence of order. It is order so sensitive, so deeply layered, that it becomes impossible to reduce to a simple straight line. And once you understand that, the ordinary world becomes more mysterious in a truthful way. Not because it breaks its own laws, but because even the simplest laws, repeated through time, can bloom into complexity no mind can fully contain. The ordinary world is full of hidden physics. The ordinary world does not become strange only when you leave it behind. It becomes strange the moment you finally pay attention to what it has been doing all along. A door closing, a cup cooling, a shadow stretching, dust floating in sunlight, rain gathering on glass, a spoon bending the image beneath water, a sweater crackling in dry air, a ceiling fan pushing warmth around a room, a phone screen glowing under your finger, a bicycle staying upright while it moves, a puddle reflecting the sky in broken pieces. These things are so familiar that your mind files them away as background, but every one of them is filled with physics. Not distant physics, not the kind locked inside giant machines or written only in difficult equations, but the quiet physics that allows the world to feel stable enough for you to live inside it. The reason a chair holds you, the reason a flame rises, the reason a refrigerator removes heat from its inside and releases it into the room, the reason your footsteps make different sounds on wood, carpet and stone, the reason a wet road shines at night, the reason a mirror reverses depth, but not truly left and right in the way people casually imagine. All of these are small negotiations between matter, energy, motion, light, heat, and structure. You do not need to invent mystery for the world to become mysterious. You only need to remove the numbness of habit. Take something as simple as a shadow. It seems like nothing, only the absence of light, but its edge can be sharp or soft, depending on the size of the light source and the distance between the object and the surface. A shadow under the noon sun can appear darker and more defined because the sun is far away and its rays arrive almost parallel, while a lamp close to your hand can create a large soft edge shape because the light comes from a broader range of angles. Even darkness has geometry. Or think about a window fogging on a cold day. Your breath carries warm water vapor, and when it touches the colder glass, the vapor loses energy and condenses into tiny droplets. The glass becomes a surface where invisible moisture turns visible, not because the air suddenly creates water, but because the water was already there in a hidden form. A fogged window is not just a blurred view, it is a phase change written across glass. Or look at dust floating in a beam of sunlight. The particles seem to drift lazily, but their motion can be shaped by air currents too gentle for your skin to feel, by heating from the sunbeam, by tiny disturbances caused by your movement through the room. The dust is not important because it is dust. It is important because it makes the invisible air readable. In the same way, steam above a hot drink is not only steam in the casual sense. What you often see is a cloud of tiny condensed droplets, forming as warm, moist air mixes with cooler air. The invisible becomes visible only when conditions change. This is one of the great hidden patterns of ordinary life. Things are constantly crossing thresholds. Water vapor becomes droplets. A solid surface becomes slippery when a thin layer changes contact. Warm air rises because its density shifts. Metal expands slightly with heat. Plastic softens when molecular motion increases enough to loosen its structure. Bread browns because heat drives complex chemical reactions between sugars and proteins. An egg turns from clear to white because proteins unfold and link together. A refrigerator magnet stays on the door because magnetic domains inside the material are aligned in a way that creates a persistent field. A touchscreen responds because your finger changes an electrical field across the glass. A camera records an image because light is converted into electrical signals by a sensor. A microwave oven warms food mainly by using electromagnetic waves that interact strongly with polar molecules, especially water, causing energy to be absorbed and redistributed as heat. The everyday world is not simple. It is layered. You live on the finished surface of countless hidden processes. Even walking is a physical masterpiece disguised as ordinary movement. Your foot presses against the ground pushes back. Friction prevents slipping. Your muscles convert chemical energy into motion. Your inner ear helps track balance. Your brain predicts where your body will be a fraction of a second later, and gravity keeps every step honest. If the floor were frictionless, walking would collapse into helpless sliding. If your bones were too soft, you could not support weight. If your tendons had no elasticity, each step would waste more energy. If your sensors did not update constantly, the room would become difficult to navigate. So the ordinary act of crossing a room is not ordinary at all. It is biomechanics, energy transfer, friction, balance and prediction woven into a motion so practiced that you no longer recognize it as astonishing. The same hidden physics lives in sound. A room has its own acoustic character because walls, furniture, curtains, corners, and open spaces absorb and reflect sound differently. This is why your voice feels different in a bathroom than in a bedroom. Hard tile reflects sound strongly, creating echoes and brightness, while soft fabric absorbs more energy and makes a room feel quiet. Your home is not acoustically neutral. It is constantly shaping what you hear. Light behaves similarly. A white wall looks white because it scatters many wavelengths of visible light in all directions. A black shirt looks dark because it absorbs much more light and converts much of that energy into heat. This is why dark clothing can feel warmer in sunlight. A blue sky appears blue because molecules in the atmosphere scatter shorter wavelengths of sunlight more strongly than longer wavelengths, sending blue light across the sky from many directions. A sunset turns red and orange because sunlight travels through more atmosphere at a low angle, and much of the shorter wavelength light has been scattered out of the direct path. The same sun gives different colors, not because it changes dramatically minute by minute, but because Earth's atmosphere becomes part of the light's journey. Even the smell of rain after dry weather has physics and chemistry inside it. Raindrops strike porous ground. Tiny air bubbles rise and burst, and small particles and aromatic compounds can be released into the air, carrying the scent you associate with the first rain. The world is always translating physical contact into experience. A smell, a color, a sound, a texture. Each one feels immediate, but each one is produced by a chain of events your body interprets. That is why hidden physics is not separate from perception. It is the bridge between the outside world and the world you feel. And perhaps the most humbling part is that many of these processes are not isolated. They overlap constantly. A candle flame includes chemistry, fluid flow, heat transfer, light emission, soot formation, oxygen supply, and rising hot gases. A boiling pot includes bubbles forming at nucleation sites, convection currents, heat transfer through metal, vapor pressure, and sound created by collapsing bubbles and moving liquid. A cracked sidewalk may involve expansion, contraction, water infiltration, soil movement, mechanical stress, and time. A rainbow requires sunlight, water droplets, refraction, reflection, and the angle between your eyes and the sun. It is not located in one exact physical place, like a painted arch. It is an optical relationship between light, droplets, and observer. Someone standing elsewhere sees a different rainbow, made from different droplets, even if both of you point to what looks like the same colored arc. That fact alone is enough to change how you think about reality. Some things you see are not objects waiting independently in space, but relationships that appear from the right alignment of conditions. The ordinary world is full of these conditional appearances. A reflection appears when light finds a surface smooth enough to preserve order. A mirage appears when layers of air at different temperatures bend light gradually, making the sky seem to pool on a hot road like water. A rainbow appears when droplets and sunlight arrange themselves around your viewpoint. A sparkle appears when a small surface sends light directly into your eyes. These are not illusions in the sense of being meaningless. They are real experiences produced by real physics, but their reality depends on position, angle, medium, and observer. And this is where the hidden physics of ordinary life becomes more than a list of facts. It becomes a way of seeing. You begin to understand that everyday objects are not dead props scattered around you. They are active participants in interactions. The table is resisting gravity through internal forces. The air is pressing on your body from every direction. The glass is transmitting some light and reflecting some. The floor is exchanging forces with your feet. The walls are shaping sound. The food on your plate is changing through heat, moisture, and chemistry. The screen in front of you is controlling light with tiny electronic signals. The room is full of thermal radiation, moving air, pressure, charge, vibration, and molecular motion. Nothing has to look dramatic to be dynamic. A A still object is only still at the scale of your eyes. Inside it, atoms vibrate, bonds stretch and relax. Electrons occupy structured states. Heat moves slowly through it. It ages, expands, contracts, absorbs, emits, responds. Stillness is often only motion too small, too balanced, or too familiar for you to notice. And maybe that is the soft conclusion this whole journey leads toward. The ordinary world is not ordinary because it lacks wonder. It feels ordinary because your attention has learned to skip the wonder in order to survive the day.